conference organizer for the invitation, and it's my pleasure to be here to show our recent work on the morphology control of upconversion nanoparticles for nanophotonics. Since it's not working. Okay. Yeah. Our research work is mainly focused on the highly doped, the upconversion nanoparticles. We improve their brightness for the nanomedicine applications. We also find very new the nanophotonics based on the highly doped upconversion nanoparticles. We further to do the morphology and function control of the single nanocrystals. And I just briefly to introduce what is the upconversion nanoparticles. For the normal Fluorescence dyes or the quantum dots, normally they absorb the high energy photons and have the emission at the low energy levels. Photons, for example, they can absorb as the blue excitations and have the emission as the red or the green. But for the upconversion, it can convert the low energy photons into the high energy photons. So how it happened? It is just through the accumulated 2 or more lower energy photons, then accumulate to the high energy photons and get the high energy photon emissions. So in this case, if we want the upconversion system, it's better we have the lead like the energy levels to make the photon energy accumulate much easier. So normally we choose some lanthanides like the erbium, thulium, or thorium. They have the lead like the energy levels, so we can easily to use them as the emitters. And to make the upconversion more efficiently, we normally co-dopped with the ytterbium as the synthesizer. It can absorb the energy at the near-infrared regions and transfer the energy to the emitters. And we co-dopt these synthesizers and emitters in the host materials and get the nanocrystals with the upconversion properties. When excited with the near-infrared, they have the emission in the UV or the visible range. But the first problem for the upconversion is they have the problem of the concentration quenching. So that's why we need the doping emitters inside of the host crystals. We find that when we increase the doping concentrations at the lower concentration ranges, the intensity will increase with the concentration of the emitters. But when the concentration is over the threshold and the emission will be reduced with the doping concentrations. This is because when the concentration is high, the emitters is easily to crosstalk with each other, so the energy could be easily transferred to the surface quenchers. So from this mechanism, we can see that we have 2 common strategies to overcome the concentration quenching. One is we can coat the inert shell to block the energy transfer from the inside to the surface quenchers. And the second one is we can use the high excitation powers to reduce the migration path length for the energies. Just one example is we use the co-share nanostructures to optimize the doping concentration in the ytterbium even as high as 60%, or thulium we can dop in around 16%. So in this case, we get the brightness of nanoparticles is 10 times compared with the 10 times bright compared with the normal doping concentrations ones. And so the nanoparticles could be bright enough for us to see the single nanoparticles and the microscopy, and we can tracking the nanoparticles movement inside of the living cells. We also can use them for the nanomedicines, for the sensitive, the acetone detections, or even for the biomarker detection by the point of care detection strips. we also find very interesting the nanophotonics based on the highly doped upcoming nanoparticles when we use the crosstalk between the different the high concentration of the emitters. So we achieve the super resolution images. And also we have achieved the nano-sized tweezers and the nano-thermometers. And then I will focus on the main topic where we concern is the morphology as functional control of the nanoparticles for the nanophotonics. With the advances of the wet chemical synthesis process, we have the ability to control the heterogeneous nanocrystals with different the structures or different compounds like the cochlear structures or the nanorods or the hollow structures. So in this case, this kind of heterogeneous nanocrystals, they have the applications for the catalysis, for the nanomedicine, or for the imagings. And in our previous work, we really want to control the morphology, how to go to the morphology control and the growth of the nanocrystals. We focus on is the sodium yttrium fluoride, which is the hexagonal prismal structures. And we find on the surface of the nanocrystals, when we synthesize them in the organic solutions, we find the two different kind of surfactant. One is the oleic acid, and another one is oleic ice. They are distributed on the surface of nanoparticles at the different phases. For example, the oleic ice is mostly distributed on the set surface and set phase. But for the oleic acid, it is distributed at the end phase of the crystals. So we can easily control the growth direction of nanocrystals by control the ratio of the two different surfactants. So if we have more oleic acid, they can protect the set phases and to choose the longitudinal growth gas nanorods. And when we have the more oleic acid in the solutions, it can protect the end phases, and we can get the transverse growth gas nanoplates. And then we want to know whether we can, because for this method is we still can see, even for the longitudinal growth, the diameter of the nanorod will still increase when we grow the different materials. This is because we have large amount of the precursors inside of solutions. So when we want to really process the one-dimensional growth, we need to lower the concentration of the precursors, and we use the hot injection method to keep the concentration of the precursors at very low, so we can get the layered growth process, like this video shows, with the protection of the surfactant. And when we keep the lower concentration of the precursors, they can achieve the layered growth. And after the growth, the first layer, we can inject another kind of the precursors to achieve the another layer of the growth for the different materials. And this is the morphology control. The TEM images we show, we can easily control the the thickness of the different layers or the number of the layers, and just change the injection of the different precursors. They are not only very uniform for the different nanoparticles, but also even inside of nanoparticles, the distance between the different parts, they are very uniform. And now we have the really good morphology control. We also have the super resolution and nanoscopy. So what we want to choose is whether we can use the the super resolution to see the different part of the nanoparticles within diffract limit. What our design is, we have the active, the optic active sections in the nanorod as the two end. So in the middle is the optical inert one. So in this case, when we scan the nanoparticles using our super resolution microscopy, we can see the two optical sections like we can see in these pictures. If we use it in the normal confocal images, we can only see the big nanoparticles is around 500 nanometers. This is because the excitation wavelength is 980. And because we can easily to change, to control the morphology of nanoparticles, we can change the distance between the active sections from 55 nanometers to 120 nanometers. From TM, we can easily to confirm this design, and also from the super resolution images, we can see the distance increased from 76 to 140. We also can control the volume of the active part because the intensity is linear with the volume of the nanocrystals. So we can use the different ratio between the different parts. So we can get the different contrast for the different part of the nanobarcodes. We call it, it is the digital nanobarcodes. And another one I want to show is also we can doping the different elements. The different elements have the different emission wavelengths. So we can easily use the color to separate even the neighbor layers from the thallium or the erbium. And also we can use the excitation power as the lengthened upcoming nanoparticles. They are excitation power dependent performance. We also can do the energy transfer, the nanoparticles. This is another one we demonstrated is we doped the lengthened can emission the different colors at the different parts through the excitation with different conditions, so we can get the single particle for the RGB emissions. So next, I want to briefly show our recent work is the anisotropic energy transfer in the nanocrystals. As the energy transfer between lengthened could be DET or the FRET models, but for the energy transfer with the neighbor eyes, we cannot to detect the signals because it's very easily quenching, and the signal is pretty weak. And even we can introduce to three-dimensional anisotropic use our crystal phase, so we can see they still have the two main space is Z direction and XY direction, but for the single unit, we still cannot get any signal. So what we have done is we introduce the repeat unit for both the Z direction and XY directions, so we can increase the distance at the Z direction and XY direction, and to see the emission performance differences. The first one what we need to do is the controlled apparent growth, not only in the one-dimensional growth, but also in the two-dimensional growth. We show the TM results here. The first experiments, we confirm the energy transfer dynamics in the two different directions. We use the neodymium, ytterbium and erbium system. The energy could be transferred from the neodymium to ytterbium and to erbium emitters. So for the energy flow, we can see for the nanorods, they can transfer from two ends to the middle, and for the nanoplate, they can transfer from the set faces to the central. And we see really the difference for the dynamics. The nanorods, it increased very quickly, but for the nanoplate, it is slowly increase the energies. And we also designed synthesis of the heterogeneous nanocrystals, and we want to really see if we have So I will quickly 1 minute. If we have 1,000 of emitters inside, whether we can see as the end phases and set phases how much for both of them. We use the ytterbium thulium gadolinium energy migration process, and finally we found that the energy is mostly transferred in the longitudinal directions, and even we change the different receptors. And we also do the simulations for this study, and we found it is mostly about the DET models for the energy transfer. And for the summaries, we focus on the highly doped nanoparticles. I want to thank our postdoc students and funding, also my collaborators. Thank you for your attention. We use the for the materials it's it's sodium yttrium fluoride, because we calculated the energy levels, and for the oleic acid ice, it is just like oleic acid. When we react it with the sodium hydroxide, it could be get the oleic acid ice. So we found its binding energy to these different phases, and it prefer to 100 phases, but oleic acid it prefer to 001. So finally we found that the distribution may be like this, but we didn't have the direct evidence because it's not easy.
That was my question.
Yeah.
And how universal is this approach to also apply it to other materials?
We try to use this method for the different elements, like the iron oxide, but we didn't successful to get the control. Maybe maybe now it's still limited to the sodium yttrium fluoride materials. We are still to do like the quantum dots, but that work is still in process. Yeah.
Thank you very much. Thank you, speaker again.
Okay. Thank you.
All right, and our next speaker is Suha Yang, and she will present about versatile phosphorus synthesis characteristics and applications.
Good morning, everyone. I'm very happy to present our research finding of the subject about versatile phosphor for their synthesis characteristic and application. I'm Suha Yang. As we know, the essential application of phosphor is igniting, but their application for context, temperature sensing, lantern figure visualization, optical adaptation, and optical data storage is also attracting much attention and is worth investigation. Usually, phosphor require doping with a specific debator to produce their daylight emission. Among the debaters, magnesium ion has received considerable attention. However, their emission changes with the host. So we should choose the host to achieve the desired emission property and application field of the phosphor. In our phosphor synthesis, we choose magnesium titanium oxide as the host, since it has promising for diverse applications. Our study also shows that magnesium titanium oxide doped with the manganese ions can also achieve for thermometry and lantern finger visualization applications. This phosphor can be prepared using both solid state reaction and solute process. This is the process for the phosphor prepared by the solid state reaction and by the solute process. When the phosphor prepared by the solid state reaction, 3 pyrolysis process occurs during heating. This indicates that the intermediate phase may be produced in the phosphor. Whereas when the phosphor prepared by the solute process, the citric acid suppresses the formation of intermediate phases while promoting the development of target phase. So a single phase phosphor is synthesized. The crystalline analysis shows that a biphase phosphor is synthesized by the solid state reaction, whereas a single phase phosphor is prepared by the solute process. The composition analysis shows that the phosphor has a FCC lattice with an inverse spaniel structure. And the composition analysis shows the atomic composition between the atoms excludes the stoichiometry of the host. And all elements are uniformly distributed in the host. When the phosphor is prepared by the solute process, a noticeable enhancement in the emission is observed. And the their emission intensity is sensitive to the change of the temperature, and which can be fitted to a linear function and expressed by this equation, allow us to calculate the temperature sensitivity of the phosphor. This high temperature sensitivity allows us to application for this phosphor in contactless temperature sensing. Additionally, this phosphor can also be used for lantern fingerprint visualization. We can see that the lantern fingerprint on the glass, silicon wafer, and plastic pieces appear visible when stained with the phosphor. We also see the lantern fingerprint on the plastic car, aluminum foil, and glass pieces can also visualize when stained with a less blue silicate-based phosphor. This figure shows that the golden detail of the lantern print appear on a blue phosphor stained aluminum foil. So our prepared phosphor show promise as a material not only for lighting, but for optical temperature sensing and fingerprint visualization. Next, I will like to present our research finding of phosphor in biodetection applications. As we know that lateral flow assay is a promising biological identification technology for the rapid detection of multiple analytes. Our synthesized phosphor is promising for this application. This is the flow assay configuration, which is composed of sample pad, conjugate pad, membrane, and a sortation pad. For visual inspection of the test information, the analytes can be labeled with fluorescence nanoparticles, such as metal nanoparticles. quantum dots. In addition, in organic nanophosphor are highly regarded as potential luminescence labels. They have unique features such as tunable luminance and high chemical stability. For the operation of the flow assay, when the phosphor labeled analyzed flow through this assay, they will be collected in the T9 and C9. By analyzing the luminous intensity of T9 to C9, the analyze can be identified. To prepare nanophosphor label for on-site rapid optical detection, these two kinds of phosphor is prepared in our lab. This is the preparing process for the phosphor. Both phosphor emitter from visible to near NIR band, which is biocompatible with the bio window of tissue. These phosphor show high thermal stability. Since our phosphor show high thermal stability, and so we can use this phosphor for bio detection. To evaluate the potential phosphor for bio detection applications, the cell viability of T24 cell is measured after culturing T24 cell in phosphor aqueous solution for 24 hours. The high cell viability shows this phosphor has no significant toxic effect on the cell. This image shows that the cells are successfully labeled with blue luminescence phosphor. The high cell viability of T24 is also measured when culturing in a high concentration of this phosphor. For test information, for this flow assay test, we use human IgG as analyze and nanophosphor as a label. This shows the bioconjugation process of the for preparing phosphor goes anti-human IgG bioconjugate. This process follows the Professor Low in this publication. We can see that the test information are clearly visualized when the phosphor is labeled. And high luminescence intensity ratio of T9 to C9 is observed. This demonstrates that our phosphor are promising material for biosensing application. In the last, I will present our research about persistent luminance for their use in digital optical data storage application. Our study showed that structure illuminate co-doppler with European dispersion can be performed in persistent luminance with a high thermal stability. So it can be used for after data storage application. This is the preparation process of the phosphor. And their crystalline property. Sorry. And their chemical state information of the elements in the phosphor. Our research found that codominant dispersion in the phosphor will prolong the luminescence lifetime of the phosphor, results in a persistent luminance. This phosphor also show high thermal stability and high moisture resistance. This is the image for our phosphor excited under daylight. And after grow image, after turn of the daylight, under excitation of UV light, and after grow image, after turning of the UV light, we can see that the luminance remain visible even after turning off the UV light for 5 minutes. The persistent luminance is the desired property for phosphor, for their useful after data storage application. The luminance of phosphor compound this application. We can see that the performance of digital optical data storage of performance of our phosphor. The luminance decreases rapidly once the laser is turned off. Alternatively, brightness and dimming when the laser is switched on and off. And we also see that the higher the switching frequency, the better the optical data storage performance of phosphor. In my talk, I have presented our phosphor for their synthesis and characteristics, and their application for contactless chemical sensing, lantern fingerprint printer visualization, on-site rapid optical palpation, and digital optical data storage. Thank you for your attention.
Thank you for a nice presentation. Other questions? I have a question about your bio-labeling applications. What are the requirements for the materials that work best there? Why did you choose the materials that you shared?
For biodetection, usually choose the phosphor have the property of high thermal stability and low toxic effect on the cell.
And are there also specific requirements on the luminescence properties?
The luminance intensity is also important for biodetection.
But the color is not very important, as long as you can just measure the intensity.
Afterglow is also important.
Okay.
Yes.
What color would you like to use?
Which material shall we choose? In this phosphor, we can see that the first one, manganese Doppler magnesium titanium oxide, it shows high luminance and high and low toxic effect on the bio cell. The disadvantage maybe is it is sensitive to the temperature.
Okay, thank you.
What's the limit of detection for the lateral fluorescence in your phosphate?
We have not yet studied this field because we have a large financial to buy the source. Yes. Thank you.
There is time for some more questions. I do have one more question on your afterglow materials. You said that if you do a pulsed excitation with a higher frequency, then it starts to work better. I didn't
Sorry.
know. It was one of the last slides.
可以帮我放到最后一页 ，the last.
Yeah, yes, this one. What do you mean exactly with it works better? You mean that it glows for longer?
Because this phosphor shows a persistent luminance. So if you the switching frequency is low, and the intensity will be decay.
Yes.
And the information will be lost. So you choose a high frequency. You can excite the lamp, they will not decrease. Before they decrease, you excite it again.
Right. So you will not really go to a zero intensity and then
Yes.
you're ready excite again. Okay, I see. Okay, thank you very much. If there are no more questions, then let's thank the speaker again. Then our next speaker is Candy Mercado, and her presentation will be about phase transformation photoluminescence studies on europium incorporation into calcite. The floor is yours.
Thank you very much. I'm Candy Mercado. I'm from University of the Philippines. And this work is done in collaboration with the University of Houston. I have to press. So it's my first time here in Phosphor Safari, and I really like this meeting. Okay, here it is. Okay, so I'm going to go a little bit slower because I arrived in this phosphor and photoluminescence inorganic material very last in this in the game, as they say. So I'm still learning on the basics of europium incorporation, and we have this material which is calcite, and we wanted to see what are the capabilities of this material. So we are the basis. We are coming from ion exchange, from an ion exchange point of view. So we're incorporating several different ions and trying to see which ions will transfer well with calcite. So with calcium in calcite. Okay, so here are the various applications. You might have heard about most of these in the earlier talks, and we'll probably hear about most of these in the latter talks. So europium doping has been widely studied. It basically has some applications in drug delivery, mechanoluminescence, in bioimaging, in high quantum efficiency phosphors, and in solid state lighting. And doping in calcite has been studied because of the very strong luminescence that is coming from europium going into calcite. It's also historically, europium is a model for radioactive radioactive elements. So you can determine the characteristics of some radioactive elements by looking at how the europium is incorporating into different matrices, inorganic matrices or minerals. So this has been a very important thing to study how europium incorporates. Okay, so this is our matrix. Our matrix is calcium carbonate, and it's in the form of calcite, as we are looking for. This is a rhombohedral structure. I was saying earlier that we are trying to see, this is the ion exchange affinity for cations, and this one is calcite. And we have been trying to see how each of these atoms or elements are incorporating or exchanging into calcite. So these two we are already done. This is in part of our perovskite study, and now we are doing this phosphor study for europium incorporation. Now this is only 3 plus, incorporating into 2 plus. So this chart here is not, it's just a rough guide on how to choose which elements you would use for ion exchange. So we are doing this progression. Okay, so we have calcite. This is calcium in the 2 plus configuration, and then CO3. Okay, so when we went to the lab, and okay, we can buy, for example, EU europium carbonate, and however, we cannot find it, so we had to do it. We find europium oxide readily available, and we converted it into europium sulfate. So now europium is in the +2 oxidation state. So we have initially it was alpha europium sulfate, and it became the more stable beta europium sulfate after heating. Okay, so this synthesis is the first part, just to convert the +3 to +2. So now we are going to do co-precipitation. We have europium sulfate and calcium sulfate. By mixing different quantities of europium with calcium here, and then putting them all together in solution, and then adding sodium bicarbonate and sodium hydroxide, we will convert it into a defined ratio of calcium substituted with europium carbonate. Okay, so this initially it was this clear solution, and then eventually the carbonate started to precipitate, and eventually we had enough precipitates to make into a pellet, and then we anneal these pellets in different temperatures, and then eventually it's looking like a light yellowish powder. So we did, this is how we do the photoluminescence sample, by mixing in clear adhesive on glass slide, on quartz slide. Okay, so the equation is like this. So we have europium substituting to some calcium into. However, it didn't actually substitute very well, or up to our expectation. Only a little bit of, so for example, we wanted to have, in the initial solution, we put 0.625, but we only got, after getting the precipitate, 0.42, and so on. So there is a difference between our prepared solution and what we got in the precipitate with respect to 8% incorporated. So after annealing, we eventually, annealing for 24 hours, we have this red emitting phosphor, which is the EU +3 phosphor, EU +3 emission. So we did what we want, we checked what we have in our samples. So these are the various annealing temperatures. And here is our XRD. So just to show the progression, is that initially we have the carbonate, the green one, carbonate, and then at 400 it will convert into europium oxide again. So the carbonate is only stable up to around this region. Okay, so now here is 10% europium in calcite. I have same story here, stable in the lower up to 350, and then converts to oxide in the 400. This 20% europium in calcite is a little strange because even if we did this several times, there is some missing. At 400 degrees, there is no. It doesn't show whether it's whether the europium is in the carbonate or in the oxide phase. So we still don't know what's going on with this one. So we decided to run it in XPS. So this is the summary table. These are the different weight percents, and these are the different temperatures. So at high doping of europium and at 400 degrees, it's not showing very well in XRD what the crystal structure is. So we did XPS because we wanted to know whether it's EU2 plus or EU3 plus at 400 degrees Celsius. And this is showing the XPS value, and it's confirming that it is indeed a 3 plus in that region. And only in the 450, I have some 2 plus remaining in the XPS value. Okay. And so we tried to do what is the actual conversion temperature for europium carbonate, but this one is done in a controlled environment in TGDSC mass spec system. So as it heats up, we get the XRD and also the mass spec of what's the gases. So it seems that at 400 degrees, it will start to evolve the CO2, and then the CO2 will catalyze the further breakdown of europium to europium oxide. Okay, and we also looked at the changes in the crystal dimension. So you can see here the different crystal radius. So when we try to do the ion exchange, we look at the crystal radii of different elements. So calcium is 1.14, and plus 2, europium is 1.31, and plus 3 is 1.08. So it is easier to, it's almost in the middle of EU plus 2 and EU plus 3, the calcium 2 plus. Okay, so we can see here the different progression in the lattice parameters. This data is also based on the XRD, just looking at the Rietveld refinement of the XRD peaks. So this is in summary, these are the photoluminescence obtained in the different substitutions. So at 450 C, if you have at least 1.25% of europium substituted for calcium, then you will get the red luminescence. And if you have 20% at 400 degrees C, you will already get red luminescence. So this is a little bit lower temperature than what they used to process europium substitution and annealing temperatures. So the photoluminescence progression of europium looks like this. Normally, okay, so this is getting higher and higher. Now this is 20%. Of course, this would be highest. But what is different from most of the europium emission is that it's only one large peak. The small peak, this one is repressed or has less emission, and this is okay. And we looked at the decay time. So this is actually not phosphorescence. This is just photoluminescence. So there is the decay time that is like 7.25 nanoseconds and 1.38 nanoseconds. Okay, so these are the two peaks, the D to F1 transition and D to F2 transition. The literature already identified this as the electric dipole transition, and this is the magnetic dipole transition. And this is the examples of photoluminescence of europium as substituted in tin oxide and yttrium oxide. And here you can see how the centrosymmetric symmetry of the crystal will affect the emission of a europium. So if you have a centrosymmetric molecule, crystal, then this section, below 600, will be more intense, and this section higher than 600, which is this 2J is equal to 2, will be enhanced if you have no inversion symmetry in the crystal. So that's a good. If you want to really be particular on the wavelength that you want to get from your signal, then you can use these two methods to identify which one you want to get the correct photoluminescent particle in your device. Okay, so these are the origins of the different transformations for EU plus 2 and EU 3 plus. We didn't get EU plus 2, even though we tried to excite with UV light in that upper picture. We only got the emission from the EU plus 3. So maybe we didn't excite it enough. Maybe we need to have a higher power excitation source. Okay, so these are just my summary and conclusions, which are what I've already said in the paper, in the presentation. And I just would like to acknowledge University of Houston and Professor Arnold and Professor Marlon. And this is my PhD student who did this project. And this is also project in collaboration with, you might think, okay, why are there some fish here? Because this is a project in collaboration with the aquacultural department, because they have some shells that are made up of calcium carbonate, and they are looking for what are the other ways that we can use these shells instead of just the traditional aquaculture ways that like decorative and so on. Are there technical ways on how to use these shells? Thank you very much.
Thank you very much. The floor is open for questions. I have a question on your luminescent spectra that you show, I think on slide 16, where indeed it seems surprising you don't see europium 2+ emission, although these are the calcium sulfate materials, right, doped with europium.
Calcium carbonate, yes.
The calcium carbonate, right. And then this one, I agree it looks like europium 3+, but it is interesting that you don't see the narrower peaks. Usually these are spectra you get if europium 3+ is not in a great crystalline environment, and maybe that makes sense as it is a 2+ position. Did you do any analysis to understand where the europium is and why the spectra are broader than you would expect?
We actually, the only analysis that we have to check what the phase of the europium is in the XPS and in the X-ray. We did not do a closer imaging of the like the cross section and each particle to see where the europium is. And this is just these are done in air and in room temperature also. But that is really very curious. We were also very curious that we did not see any EU+2 because from precipitate to 350 there should be some form of blue luminescence. So I don't know, do we need to excite with a higher UV light? That's our thinking that maybe it needs a higher UV light. We haven't done that.
Usually europium 2+ is quite luminescent. Did you also try the lower concentrations of the europium samples to excite with the UV light?
Yeah, yes.
Also the 7 nanosecond decay times seem really short for europium 3+, so there is something funny.
Okay.
Maybe one other question then on your analysis on understanding if the europium is in this oxide phase or the carbonate. Did you also try with luminescence there to understand in which phase it was? Because the europium oxide phase should have very distinct luminescent peaks.
Oh, just testing the luminescence of europium oxide. Actually, we did not do that, just the europium oxide. We didn't do the luminescence. But that's a good weekend.
Might be easier than XPS. Any other questions? If not, then let's thank the speaker again. Then it's time for the final talk of this session from Professor Fushuang Yang. And I believe... Sorry, Zhang. Sorry, apologies. And he's professor here in Taiwan, so I guess he's close to home. And he will talk about the top emission organic light emitting diodes on stainless steel foil. Please go ahead.
Okay, this topic I will talk about the top emission organic light emitting diode fabricated on a flexible stainless steel substrate. So this is a special topic. We first time fabricate the OLED on the stainless substrate. It's a very thin foil. Okay, my name is Fushuang Zhuang. The other author are Duan Youxin and Hong Kai Chen. Okay, my master student. We come from the Department of Electro-Optical Engineering from National Formosa University. My university just located in middle Taiwan, just a little south to the Taichung, okay, Taichung city. Okay, my topic will talk about the cathode structure on the OLED diode, and in this topic we focus on the orange color. So at first we study the double side emitting on glass substrate. Then we start to using the stainless steel substrate to fabricate the OLED. But we need to polarize and insulating the substrate because it's a conductive substrate. So we have to do some polarization on the surface. Then next we study the detail about the organic layer to optimize the device structure. Okay, so organic layer and also whole transport, whole injection layer to adjust the device thickness. Then the cathode thickness is also important for the top emission devices. So I think it's a well-known device, OLED. Now it's already commercialized in TV and cell phone by iPhone and the Samsung company. So this is the experiment procedure for the top emission. Also, bottom emission, the similar procedure. So the first, I focus on the stainless substrate. So cleaning in acetone and isotropic and by ultrasonic cleaning. Then because the stainless substrate is too thin, it's very flexible. So we combine with the glass first to become solid. Then we can transport and do the experiment. Then UV ozone cleaning on the stainless substrate. Then spin coating flat layer, organic solution layer, TOC 100. This is the product number. Okay, from the Taiwan company. Then spin coating on the substrate surface. Then continue to deposit the anode metal on the surface of the flat layer. Then continue to deposit the organic and the cathode layer. After the device finished, then we transfer the device to the grow box for the encapsulation for the package. Then continue to measurement the characteristic. This is the top view of the device. This area is the emitting layer. Some area for anode, top for cathode. The real cathode layer, aluminum silver, is in this area. Okay, then square area is the organic layer. So we by metal mask to try to define the device pattern for each area. Okay, this is the measurement by PR650 for the luminescence and the spectrum measurement. The K30 2400 for power and current measurement. Okay, this is our device by computer control. Also, first topic about the cathode structure. Okay, this is the Venn diagram of our device. So from the this is the first on glass substrate because we need to test the anode on the cathode material first. Okay, so at first we study on the glass substrate. This is a simple emitting layer, ALQ3. It's a well-known material. So we just test the cathode layer and anode layer and the cathode layer. So this device we using I-turbium to the electron injection layer. On the cathode layer, we use aluminum and the silver, okay, to adjust the optimal devices. Okay, so this is just for beginning test. Okay, so the cathode layer will have an important effect on our device results. Okay, so we can discuss about the I-turbium and the aluminum silver, the thickness. Okay, so we find a little aluminum layer will have a higher luminescence intensity. Okay, so if we only have only the silver as the cathode, the silver not a good cathode or material, because the silver atom will diffuse into the organic layer. Then the device lifetime and the characteristic will be worse, will deteriorate the cathode surface. Okay, so we have put some deposited some I-turbium to help suppress the diffusion of silver. Okay, then we find not good enough, so we continue to employ the aluminum thin layer between the I-turbium and the silver in the cathode layer, so we can get more brightness luminescence. Okay, so also the I-turbium material is very good for reduce the energy barrier for electron injection. So the injection to the TBBI organic material. Okay, then the middle aluminum layer also can enhance the silver dispersion. Okay. Then because next topic we will study about top emission device structure. So we try to optimize the top side emitting. So we study the double side emitting, bottom emission and also top emission. Try to adjust the cathode layer structure. Okay, so so the second topic we try to study the two side emitting on glass substrate. Because finally we want the top side emission, okay, on stainless substrate. Okay, so this double side structure, we try to decrease the thickness of aluminum and silver, try to improve the top emission to become a little transparent devices. Okay, so we fabricate on the glass substrate. And host and orange dopant, this is the organic material. Okay, so this double side device is okay. So we employ the aluminum and the silver and the 15 thickness of the cathode layer. Try to get the top emission. So we can find the results. So we measure 2 times. The bottom side measure 1 time and the top side measure 1 time. Then we got the 2 results. But the bottom emission luminescence intensity will be still higher because the ITO is very good transparent material. So the bottom side luminescence is higher. But we got a little top emission already, okay, by using the this cathode structure. And also spectrum, top emission spectrum due to the microcavity effect. So the spectrum width will be little thinner. Okay. So this is the photo, the emission photo. Okay, the bottom emission brighter. brightness is higher. Top emission, the emission we call a little weak. So this due to the cathode layer transmittance not so high enough. You can see if the aluminum 15, silver 15, then the transmittance only very low, about 4.6%. So for top emission, the cathode layer thickness is a little too thick. But if the cathode thickness is too thin, the conductivity will be lower. The device results also not good enough. So in the future, we continue to study the cathode layer structure. The third topic, we start to study the OLED on stainless substrate. Okay, so we need to spin coating, insulating, and the planarizing layer. Okay, so this is the spin coating method. We use the TOC 100. This material is a solution type. So spin coating on the stainless substrate first by spin coating. Then hot plate to cure become solid film on the stainless. Then fabricate the organic device structure, anode, EML, and cathode, okay, on stainless substrate. Then continue to do the encapsulation, okay. So my student, they find a very good method to spin coating the planarization layer on the stainless substrate. If they just drop one drop on the stainless surface, then spin coating, they find the surface roughness also still not good enough. So the device will fail. So they try to slowly drip the solution to cover the whole stainless substrate. Then finally they get a very good planarizing layer. Okay, so this is the device emission. Okay, so the stainless substrate is very rough. So by AFM measurement, you can find the roughness is very bad. There is some scratch line on the surface. Then after the planarizing layer, you can see the roughness much improved. The R maximum value and RA value decrease to a acceptable region. Okay. So we continue to adjust the thickness. So this is the device structure we fabricate on the stainless substrate with aluminum as the anode layer, then also titanium and the silver as the cathode layer. So the light will reflect from the anode and go through the top to go through the cathode layer to the top region. So this side we call it top emission. So the total organic layer thickness we need to adjust the optimal or better results because the microcavity effect is very important, very pronounced in the top emission devices. Okay, so we can find the thinner thickness, total thinner organic layer. We get more bright, more higher luminous intensity. Okay, so also the spectrum a little shift due to the microcavity effect. So sometimes we got the green color, sometimes we get the orange color. Okay, due to the organic layer thickness. Okay. Then the the whole transport layer TAPC is also important. We just a little adjust the optima, the thickness, try to get a more better results. Okay, so we compare 10, 20, 30 nanometer for TAPC, then we can get a higher luminescence. Finally, okay, also from our experience, we find that the cathode layer is cathode layer thickness is very important because we need to should be transparent for the top emission. So we a little gradually decrease the thickness of the cathode layer. So because the transmittance for different thickness, we can find thinner aluminum and thinner silver, we get high transmittance. I think it's a well-known idea. Okay, so if the thickness is too high, then the transmittance is low, so the emission will become weak. Even the device structure is good, but the light cannot come out. So just the cathode layer is important. Here is the detail, the value for the transmittance. Okay. Okay, so we find that the silver 6, aluminum 6, silver 8 nanometer, we get a higher luminescence. Okay, efficiency or higher. Okay, finally, also we a little adjust the HATCN hole injection layer. Really, actually, this HATCN and TAPC, both layer is important for the device structure. Okay, so we just a little increase the whole injection layer HATCN, so we can get more and more higher luminescence. You can see if we a little increase the HATCN, then we get 1,000 more or CD per square meter luminescence. So we got a very good brightness device. Okay, so I think time is enough. This is our conclusion. And we demo the results of our device. We put combine together on the stainless foil to become a large area. This is the separate device, is one piece with the package. This is without the package. We demo it's really flexible on stainless substrate. Okay, thank you very much for your attention.
Thank you very much. Other questions?
This one? Yeah. From the anode, it is reflective. And the top cathode also a little reflective. So these two lights will resonate inside the cavity. So we call it a microcavity. Okay, so the microcavity will related to the thickness between the anode and the cathode. Huh?
How is this kind of resonate reflection back and forth to change the color of the appearance?
Yeah. Yeah. Because the thickness, the wavelength is related to the total thickness between anode and cathode. So the microcavity, like the laser diode, the cavity length is important. Yeah, it is due to the resonance intensity. Some wavelengths will enhance. Yeah. Okay. Yeah. Good. Thank you.
Last question?
you use the stainless substrate to fabricate the oil. When compared with the solid one, the substainless substrate decrease the EQE or something.
You mean compare with the glass?
Yeah.
Yeah. First question, we only focus on the current luminescence yield also here. Okay. I think the relationship is very similar. So I don't, because time not enough, so I didn't emphasize the efficiency. And the EQE is more difficult for our lab to measure. We don't have integer ball. For the quantum efficiency, we need a good equipment to measure the EQE. Yeah, so a little difficult for our lab to measure the data of EQE. And then on the stainless substrates, because there is organic flat layer, planarization layer, this is organic material. So the quality not better as glass. Glass, the ITO on glass, the surface roughness is very, very beautiful. Okay, but we put we spin coating planarization layer on the stainless substrate, so the quality not good enough. Even the AFM a little improved, but I think the roughness, the data not as good as the glass substrate. So the device, then we deposit the aluminum as the anode, right? The anode layer we use aluminum thin film as the anode. The aluminum function also not good, not lower as the ITO work function. So the aluminum layer as the anode not so good for the device. I think it's an important issue. And also the roughness, the aluminum layer on the planarization layer surface is also important. Yeah, I think some issue, then we cannot compare with the glass substrate. Yeah. Okay.
All right, let's thank the speaker and all the speakers of this session again, and then it's time for a coffee break.
Okay, yeah, good. Thank you everybody.
After that will be posters, I think, next door in that room. Thank you, everyone.
So for his presentation, the computer,
Oh, computer.
it was there. Okay. So good afternoon. I hope you had a good lunch. And so the first presentation of this afternoon will be held by Professor Jin Yan Huang. Hua. Jin Hua. I'm sorry, my it's difficult sometimes for me to pronounce it different, but I'm sorry if I pronounce it wrong.
No problem. So different culture, different countries.
And he will speak about the aggregation induced emission of plasmonic metal nanoparticles.
Okay. Thank you very much and for the introductions. So and also thanks to organizers for giving me the opportunity to present the research in our group. And my name is Tsinghua. So in Taiwan have Tsinghua universities, right? The same one. So I'm from Singapore, and we also have institute in Suzhou. So I take position at both places. So for today, because my area is on plasmonic materials, so for today I'm going to present how we use aggregate and aggregation of plasmonic nanoparticles to achieve enhanced emissions, that including 1 photon and 2 photon emissions. Oops. No. Should be what done? Which direction should I? Yes, which direction I should? Looks freeze. If it doesn't work, maybe I can use mine. Is it working? Maybe I can come over here. Take some time to install the drivers. You don't have to do anything as long as just plug in, and it takes about 1 minute. Mm, 是我的那个吗？哪个？里面有插进去啊？
It's happened with me too.
Yeah.
My talking to
You also have to.
it happened with me
Yeah.
too.
Maybe I just use my own computer. If some problem, I can just use my own computer. It would be easier. I should have done a test. No. Yeah, not computer. What is it? You have documents on this one, right? Is this one, yeah. Okay. Just any USB, just anyone.
It's working, yeah.
It's okay.
Sorry for the delay due to the problem. So first, I will give a brief introduction about what is plasma resonance. Plasma resonance is using for the local metal nanoparticles. They display some kind of unique properties, and it's due to collective oscillation of the conduction binding electrons. So the consequence of this kind of local plasma resonance will going to result in the local electric field amplifications. In particular, if we're going to have a local field amplified, so you have a dimers or aggregate, the local field amplification would be much larger compared to the monomers. And then for this kind of effect, because local electric amplification, we're going to create and modulate the optical properties of external chrome force or the metal nanoparticles itself. So the consequence is how we're going to utilize this phenomenon to amplify, to enhance the optical property or emission of the molecules. So we know, and based on this general and Jablonski diagram and of the molecule involved in the emissions, we know the emission efficiency. So it's the product and of the excitation efficiency and also the quantum yield. The quantum yield determined by the competition between the radiative and non-radiative decay rate. So when you are putting a chrome force nearby to the metal nanoparticles, so both the electric field amplifications were going to cause the enhanced excitation efficiency depend on one-fold or the two-fold excitation efficiency. At the same time, the radiative decay rate were going to be enhanced. If radiative decay rate enhanced based on these formulas, they were going to beneficial to the quantum yield. At the same time, you're going to have any transfer from the chrome 4 to the metal nanoparticles. This one actually contribute as the increased non-radiative decay rate. So therefore, and for all, the first two factors will help to enhance emission, but the third one is actually it is bad. So we need to optimize for all these three factors depend on distance between the chrome force and the metal nanoparticles. So therefore, to achieve the overall optimized enhancement effect, we need to optimize the distance. So we first demonstrate the concept and put this is use silver as a core and chrome F fluorescent as chrome force. So we just silicon share and to adjust distance between your chrome force and metal nanoparticles. So adjust the thickness and we achieve the overall enhancement. For example, and we get and in the very short distance, we get the quench, and the longer distance also less enhancement. So we get optimum enhancement about 5 times enhancement. This is for core size or 75 nanometer. For 52 nanometers, we get similar effect. The overall, if we take all this metal nanoparticle with different thickness, the fluorescence intensity increase, but their lifetime they can become shortened. So this can only to be explained by in terms of the enhanced increased radiative decay rate. So for this kind of nanoparticle, as you can see here, the intensity is stronger, the lifetime is shorter. Lifetime is shorter, that means shortened excited lifetime, so therefore be more stable. So for this kind of nanoparticle, it's particularly very useful in the bioimaging probe. Because for this kind of enhanced increased excitation efficiency comes from two factors. One is due to the enhanced excitation efficiency. The second one is due to increased quantum yield. So therefore, you can imagine you want to get a larger enhancement. It's better to achieve for those chrome force with a lower quantum yield, we're going to have larger enhancement effect. So to utilize the phenomenon, we actually will first because when you put chrome force, first thing attach gold nanoparticles. So first thing this we know the rhodium molecules and has reasonable quantum yield. Once you attach them, they will become totally quench, so the quantum yield will decrease. Then you use another silver nanoparticles with the here to enhance them, as you can see here. Once this is the free molecules, once you put a gold nanoparticles, it will be quenched. Then use another particles and we're going to enhance. Of course, we adjust the thickness and to optimize. So the overall, as you can see, the enhancement will still at the thickness about 10 to 20 nanometers, get optimal enhancement. Overall trend at the same as before. And the major effect and the in terms of enhancement factors and versus the quenched ones were up to about 100 times. Of course, and compared to the free ones, it's only 4 to 5 times. So for these ones, we get metal chromophore first and quenched by gold nanoparticles, then enhanced by silver nanoparticles. So this looks like nice, but is actually in terms of applications is not very useful. So to make it simple, we actually with the same nanoparticles to quench and also enhance them. So therefore, we use in terms of gold nanoparticles or gold and outside gold is quotient nanoparticles. So with steel and with rhodium molecules attached to this kind of quotient nanoparticles, first thing, the fluorescence, attach them, fluorescence will be quenched. Then we use another small molecular system to get them coupled. The coupled aggregate. When they aggregate, because the local electric field will much significantly enhance, as you can see here. Once the form of aggregations, the fluorescence intensity are significantly enhanced. So the fluorescence is significantly enhanced. So it depends on, so we have demonstrated this is the work for gold nanoparticles, with gold, silver, and quotient nanoparticles. So it depends over fluorescence intensity compared to quenched one or compared to the free ones, you get different the enhancement. So if, for example, if from the second and from here to here, because at the very beginning we quench the fluorescence, so this is equivalent, we're going to quench the background or quench the noise. And then from here, is this molecule, some kind of detection molecule, when we add them to, will cause aggregations, so the overall intent will be intense. So for here, as you can see here, this kind of technique will allow us to achieve very high sensitivity because you improve signals and suppress and background at the same time. So if we, for example, if for this thing, if we, in terms of detection, we'll be able to achieve a detection limit and up to 3.4 picomolars. So this is for this kind of phenomenon. It's just when you add something, will cause aggregation, get fluorescence intensity from pre-quenched one to significantly enhanced. So we're going to have a much larger enhancement effect. So for this kind of concept, we have is not for here is demonstrated the works for gold nanoparticles and gold and quotient gold silver quotient nanoparticles. It also works and for the silver nanopart of different size. So we tried on different size to explore which one is the best. So in terms depends on what kind of enhancement factor you are looking at. So we found out for the smaller silver nanoparticles compared to the quenched ones have large enhancement factors, but for larger ones is actually for the overall fluorescence intensity. So for here I just want to demonstrate gold nanoparticles, silver nanoparticles, or the quotient nanoparticles, they all work. So based on this concept, and we can utilize and for various applications. For here, I will only demonstrate on one type of application. For example, now is gold nanoparticles, and we use the photosensitizer, like porphyrin molecules. So once you attach them, and their fluorescence intensity and will be quenched. No matter 1 photon or 2 photons, as you see, the green one, free one, attached to them will be quenched. Then we add another molecule and systemic molecules. Once you put them cause aggregations because the excitation efficiency are significantly enhanced. As you can hear, the quenched one will going to enhance by 24 times in terms of 1 photon excitation fluorescence. For the 2 photons will be enhanced by 47 times. So the fluorescence intensity are significantly enhanced, but at the same, for example, for here, this is the free one, this is quenched ones. So the intensity will significantly enhance. For here, the intense green one, red one, as you can see here. And from the this one, the lifetime will even become even shorter for the strongest one. So and in terms of stability, because lifetime it will become significantly shorter. If you compare the photo stabilities, is about 23 times and enhanced. So for here, as you can see here, the intensity will enhance about 24 times, but their stability will be enhanced and by 23 times. And also for both and 1 and 2 photon excitation emissions. So because due to enhance the excitation efficiency being enhanced, we know photosensitizers has been known as the cancer therapy drug molecule because they can generate central oxygen. So for here we compare, and this is the aggregated ones, and this is the free one. So this is normal drug molecules. So we put in the golden nanoparticles, and it will be quenched, so the efficiency will decrease. But once the form aggregate, was significantly enhanced. So this will, at the same time, and the photothermal effect are also significantly enhanced because of the enhanced excitation efficiency. Will allow us to do, because the emissions is in the is radio emission. So 1 photon, 2 photon, and emission, and also the cancer cell killing efficiency are significantly enhanced compared to those free ones or those kind of aggregated ones. So this is in terms of 1 photon emissions. In particular, based on the similar concept ideas and our group found another unique phenomenon. We found out silver gold nanoparticles with no metal nanoparticles generally are long fluorescent, no matter under 1 and 2-fold excitation. So our group and accidentally found out once they form the metal nanoparticles, silver gold, once they form the aggregate, the 2-photoluminescence are significantly enhanced, could be enhanced by up to several hundreds to thousands times or several orders of magnitude, depends on the single particle level. So we have done, discovered this phenomenon to be universal and also demonstrated in the chemical and biological sensing and demonstrate them and in the killing it is bacteria and also killing the cancer cells. We'll also conduct spectroscopy and various spectroscopy to study the mechanism. But for here, I will briefly introduce and how this phenomenon is universal and how we apply them into biomedical applications. So we found this kind of phenomenon is actually accidentally. So we added the silver nanoparticles. We found once we add conjugate polymers, because silver nanoparticles has negative charge, is negative. The polymers positive charge. Once you add them, you find out the solution will change the color. So it is because of the formation of aggregate. So if you look at it there and under the thermocycle lasers, as we can see here, and before adding the polymers, it's all flat, so no intensity. When you add the polymers to induce the aggregations, the 2-photoluminescence are significantly enhanced by about 51 times. So if we choose one of the samples to conduct and the excitation power dependence, we find out it's actually is involving the excitation of the 2 photons based on the slope is 1.9, very close to 2. That means the 2 photons are involved in the excitation process. So we demonstrate, and this was just silver nanoparticles. And later we have tried and gold nanoparticles and of different size, silver nanoparticles of different size. We tried gold, silver, and caution nanoparticles. We use polymers with small nanoparticles and as glue or the carbon agent to cause aggregations. So as we can see here, and for gold nanoparticles, and we all induce different extent of the enhancement. Because this one uses polymers. For this one, we also silver nanoparticles. The enhancement factor is not very large, and that's because at the very beginning, and the metal nanoparticle we synthesize is not so nice. So they have already pre-aggregation already. The later is another reason is because we use polymers. Polymers is larger polymers, and for here and with this caution nanoparticles, we use small molecules and induce aggregation. The small molecules, and so therefore metal nanoparticles and interaction are stronger. So therefore, as you can see here, enhancement were up to 800 times enhancement. So instead of using small molecules, we use DNA as carbon agent because DNA, the strength and can be adjusted. So therefore, you can adjust, the length is adjusted, the carbon strength will be adjusted. So it depends what kind of nanoparticle we can use. If you use 21 nanometer gold nanoparticles, are going to enhance about and up to with shorter distance get 100 times. 41 nanometers and get a larger enhancement effect. But anyway, for all different sizes, and the shorter the distance, the linkers, the stronger the enhancement effect. So this kind of phenomenon is actually very useful in terms of biological application because this small metal nanoparticle, the many chemical and biological important species can cause the aggregation of the metal nanoparticle. Once they form the aggregate, the 2-photoluminescence are significantly enhanced. And also we know for 2-fold excitation is particularly very useful in the biological application because deep penetration into the biological tissues. So therefore, in terms of it's very useful in terms of bio application. So if we compare the 2-fold method with the normal and colorimetric method, as you can see here, very subtle change in the UV exchange spectrum, we can cause dramatic change in the 2-photoluminescence. So therefore, it's has much higher sensitivities. So we have used this one to demonstrate, for example, this one the detection of thrombones and compared to this our 2-fold method, this one based on the UV, and the detection limit was 5 picomolar, 200 times better than the conventional method based on the UV or the color change. Similarly, and we can use this method to detect very subtle change in the aggregate structures. For example, we detect single base mismatch. So we use gold nanoparticles, modify the one gene strain, this is another gene strain, this is the target. Once you add the target one and commensurate to both, then you will cause aggregation. Your photoluminescence can be dramatic enhancement, as we can see here. And with room temperature, we can easily separate this fully complementary. Even one single base mismatch can easily separate and at the room temperatures. So this is in terms of sensing, and also in terms of killing the bacteria. For this here, the gold nanoparticles and aggregate on the bacteria. This one gold silver quotient when aggregate because two photoluminescence are significantly enhanced because enhanced excitation efficiency. They're killing the bacteria and it was much more efficient. And for different gold nanoparticles, gold silver quotient nanoparticles. Well, the last work I want to present is for here. If we have is golden nanoparticles, so outside with charge with positive and negative charge, and then we'll absorb the docks. So this is drug molecule. So then at a different environment, if in cancer cell environment and for the normal cell environment, the pH are slightly different. So in the cancer cell environment, we're going to release the drug will form an aggregate. The two photoluminescence are significantly enhanced, and also the drug, cancer drug release. At the same time, the photothermal effect will be much larger. So because this one and the overall effect, and for the imaging part, I'm going to ignore. For here, I just compare. For this, this is cancer drugs. So without cancer drugs and without attaching to the metal nanoparticles, the killing cancer cells is almost the same. Low metal cancer, normal cells or cancer cells. And then if we put them in the dark, attached to the metal nanoparticles, then the normal cells more friendly. By being 86%, the cancer cells no effect. Under the lasers and for here, and then you can normal cells no effect. So cancer cells killing efficiency are significantly enhanced. So by attaching this drug molecule into the metal nanoparticles, because this kind of aggregation enhancement effect, we're going to achieve overall and toward cancer cells, significant efficiency are significantly enhanced, and also, but health cells will not affect. At the same time, we'll be able to identify them with 1 and 2-fold imaging. That means you will be able to identify the cancer cells and kill them on site, much more effective. So that's all I want to present and for today, and we have demonstrated in our group, we found a phenomenon. One is the normal way, and for the chromophore molecule, they attach on the metal nanoparticles. So once they form aggregate, the 1 and 2-fold emissions are significantly enhanced. In addition to that, we also found for the metal nanoparticle cell without external chromophores, once they form aggregate, the 2-fold photoluminescence are also significantly enhanced. So for all this one, due to the aggregate, for this, both phenomena have been utilized for various of biometric applications. So in the end, and of course, thanks my students, and that's for the student and postdoc has been involved in the work I presented, and also my collaborators and working on the bacteria and also biological experiment and collaboration by this and our colleagues, and also the funding agency for their support. Okay, thank you for your time and attention. Thank you.
Professor, for your very nice presentation. So, questions?
Yes. Thank you.
Yeah, thank you very much. Very good talks. I have very kind of small question.
Yeah.
Maybe page 12.
Page 12.
Yeah, you investigated the IS, enhancement factor and the particle size.
Yes.
And the interesting point is that 55 nanometer shows
yes.
the best. I expect a smaller particle shows the more surface area for its volume, right? So I
yes.
expect a smaller particle show more enhancement because in the aggregation. But why 55? Why middle is that?
That's a very good questions, and so far there's no definite answer for your question. So the overall it really depends because for here in terms of enhancement, so it depends on the emission before the aggregation and after the aggregation. So the overall and in terms of plasma resonance, the larger particles have the larger enhancement. So generally and for the larger particles in terms of intensity should be stronger, but because what is the ratio at the same time is before the aggregations and also could also increase at the same time. So both the denominator and numerator both will increase when you increase the size. So then somehow y is particular this size, then probably we need to care for and calculations. And also I have to admit, and for this experiment, 50 times or something is not very accurate because depending on the experiment, because the enhancement is huge and after aggregate. The major problem is the bottom up before the aggregations. So when we prepare samples, ideally we want them and very well model dispersed. But in practically, maybe that also forms the aggregate to some extent already. So this will make the denominators larger, make enhancement much larger. So that reason for this one, for example, this one we have done very nice. But for this one, is our very preliminary, at the very beginning, we just want to demonstrate the concept. So not really.
No problem. Yeah, thank you very much. Thank you.
Yes.
Yeah, thanks, Professor Xu, for your very good talk. And I want to know whether the size of the cluster after the aggregation, whether the enhancement have the relationship with the size of the cluster or not.
Yes, of course. Yes, thank you. That's a very nice question. We have done that work already. We have done the single particle and work.
Yeah.
So when you have like monomers and to form the dimers, so we enhance about 7,000 times. Then
really?
you go up to the trimers, then we're about 5 orders of magnitude. And also when you form like trimers, it also depends on the linear trimer and also the triangular, the geometries, and also is all different. So in terms of that, we need to conduct a single particle why single particle spectroscopy is important because you know exactly what kind of geometry gives the strongest enhancement. Then based on this one, then you can practically, because when this is single particle study, and in the real situations, when you form aggregate, you form all different types. So if you can intentionally prepare some geometries, some type of aggregate, then you will optimize the enhancement significantly. Yes.
Okay.
So that reason, when you do the solution, we only get about less than 1,000 times. But on single particle level, we get 5 order magnitude, 6 order magnitude. Yes. So in solution, it's the average of all the possibilities.
Yeah. Okay, thank you. Yeah.
Yes, thank you.
So thank you, Professor, for your nice presentation. Just a question that I'm seeing your presentation. It's concerning about the thermal effect in your sample, in the term concerning the luminescence and the effect of the heating, for example, the sample.
Yes. For which one you're talking about? This one, or you are talking about
No, generally.
In general. Okay. And generally, because we are conducting experiments and in the solution case, we try to make sure and it is that the power is lower and also we're also stirring, so the photothermal effect and it is not so large if we want to know how much enhancement effect. But if we want to in terms of application, your intention to heat them up, then you will see the temperature change and up to 54 times. And also, you actually thanks for pointing a very important question. In this kind of experiment, the photo heating effect is very important. In particular, we conduct, for example, on single particle spectroscopy and your thermocycle lasers, so we have to make sure that the power as low as possible, so that you will not melt them, and if you want to melt them, they will be going to change the shape and accordingly. So usually we're going to check their morphology before and after experiment. So we usually look at their scattering is equivalent to the absorption spectrum. So if they change the shape, the scattering spectrum we're going to change accordingly. So we want to make sure and the scattering spectrum remains the same before and after experiment.
Okay.
Yeah, so make sure, and that's very important ones, and it's also the challenge we are facing if we want to know and it is real exact enhancement effect. But this one will not affect applications because which as known as increase the temperatures and get the enhancement and do but and after that you don't want to them and stay there forever, because once you achieve the enhancement effect, you actually won't get rid of them. So sometimes and it's good to maybe you after using them, you are using the light to damage them, to get rid of them. That's also maybe the disadvantage could become advantage. So really depend on the particular application. We'll always find a way to cater the applications. Yes.
Okay, so thank you very
Yeah,
much. Thank
okay.
you very much for
Okay,
your
thank
nice
you.
presentation.
Okay, thank you.
So, so now it's Professor Chi Yang Huang. I'm sorry if I pronunciation not very good, but he will speak about the interplay of dislocation and epitaxial strains in UV, ultraviolet C light emission diode epitaxy.
Yeah, thanks for your nice introduction. And the committee invited me to give this talk, or it isn't even not the Safari stuff, not the phosphor stuff. It's actually more epi stuff. All right, so first I got to thank my previous collaborators, especially in ITRI, because actually my work in my previous career, which is in ITRI, and we have also a lot of meaningful collaboration with the Japanese substrate supplier sales and a German institute, Ferdinand Braun Institute, and the National Taiwan University for their meaningful TEM characterization. All right, so here's the outline. So I will start with, probably you're not very familiar with that, about why we need UVC LED and what kind of difficulty we have encountered while we're building up the UVC LED API, and how we solve this problem, then give you some future outlook. So let's start with the emergence of the UVC LED API. So while talking about the UV LED API, we usually think about the nail curing, but actually that is UVA, which wavelength is around 300 nanometer. And this is actually a quite mature technology that you can buy a really nice nail curing machine in the convenience, probably not in a convenience store, like in a B&Q. Anyway, so this is pretty already mature, but while we're talking about the UVC, it's actually about for the wavelengths in the 200 to 280 nanometer. This wavelength is actually not very familiar for most of people, but it's actually getting popular in the past 20 years because the Minatama Convention would like to ban the mercury in the future. So we don't have a we need something other than the mercury lamp as the UVC light source. So we turn to the argon-based UV LED. And the real demand comes from probably, yeah? The real demand really comes from about like 4 years ago. Everybody know what's happened? Yeah, the COVID-19 that raised the people's concern in the sterilization at home. So the market demand start booming. So probably you have heard of some of stuff in your school or in your home. So the UVC LED is small and fast switching. and safe because it doesn't contain any mercury there. So now it's incorporated in the water dispenser, house appliance, hospital, and something like that. I also buy one of these water dispenser with UVC LED in my office to in memory my work before. Anyway, the market is actually booming, and it's expected that we have a CAGR for 35% every year in the next 5 years. However, the efficiency of the UVC LED is actually miserable. For the older visible LED in blue and the visible spectrum, the efficiency is around 50%. That is for an ordinary LED bulb you can buy in the B&Q. But for the UVC LED, the efficiency even now today is still like a 4 to 5%. It's only 1/10 of the market string of a visible LED. Even the champion data just announced a few months ago is probably about 12%, and that's the champion data. And for the real competitor, the mercury lamp is around 20%, so still far away for a total replacement. And why? So let's start with a close look between the conventional visible. Just take blue as an example, visible InGaN-based LED and the UVC LED structure. They might look similar at the first glance, but it's pretty different in detail. So the first for blue LED, the GaN template is a very mature technology. But the aluminum nitride template is actually pretty difficult to grow because that's something we actually never tried in the past 20 years. And the second, for the N-GaN, grow on the U-GaN is a coherent grow. If you have a good GaN template, you shouldn't have any problem with your N-type GaN layer. However, for the NL GaN, it's growing on different materials, so you need to take off the epitaxial strand stuff. And but most importantly, for the P-GaN contact, for its band gap is about 3.4 electron volt. It is transparent to the emitted light, but for the UV, it is absorbing. So that's the key 3 reasons why the UVC efficiency is so miserable. So let's start with the first problem to deal with, the aluminum nitride template. To make the template better, it starts with the tool innovation. So this is some common MOCVD supplier you might heard of if you are a crystal grower. And the second, people are trying to develop a new growth technology, probably something called a pulse-free precursor. Anyway, it's not the point here. And some people also trying to do a pattern, the substrate, to annihilate the dislocation during growth. However, any of them, they are all easily imagined, but they all have a strong risk because you need to grow a quite thick outGaN to reduce the dislocation density. So it have a very high risk of cracking. So for a 2-inch wafer of UVC LED, you might squeeze 10 or 100 good chips out of the wafer, but it is not for production because probably the yield is less than 20% or something. So there's a new modern innovation in the aluminum nitride technology. It's called thermal annealing. The idea is simple and very brutal. So we just deposit a low quality aluminum nitride buffer on sapphire and raise the temperature up to 1,700 to release all the defect strength, so make it like a single crystal. And then some people also try to combine with the epitaxial growth on the pattern substrate to make it even lower defect density. So this is the common TDD threshold dislocation density versus the aluminum nitride micron. You see the thicker you grow, you have a lower TDD, but you have high risk of cracking. So with such HTA, high temperature needle technology, we can reduce the dislocation density 1 to 1/10 with similar the template technology. And the dislocation density is actually approaching the current GaN template technology. So people is very optimistic about this technology, but however, things doesn't go that smoothly. All right, so although the HTA buffer have about 1 order lower of the dislocation density, we expect the internal quantum efficiency should go up to like 5 times or 10 times. However, the things doesn't go that easy. Although it suppresses the dislocation density, theoretically, it should improve your IQ as well. However, there's a big issue. The thermal strength change because of the change of the process. All right, so here is the conventional process in the epithelial growth. We grow aluminum nitride buffer under low temperature, then grow a high temperature to reduce the dislocation. And because the CTE, the coefficient of thermal expansion of a sapphire is larger than aluminum nitride, this kind of temperature raising stuff bring you the tensile strength. However, if you do the high temperature anneal up to about 1070 degrees, so actually we are preparing your substrate at a higher temperature. So the whole strength, the direction of strength just changes sign. So the second layer become compressive. So now we don't have an issue of cracking. People is very happy about that. However, this kind of compressive strength makes the originally compressive N-alkane even more difficult to be prepared. So now a high quality buffer not necessarily provides you a high quality epi in the end. So this is an example of the aluminum nitride grown with alkane on that. With the conventional one, the aluminum nitride template, the FWHN, it's wide. It means the crystal quality is low, and the resulting alkane above that is in the similar level. Now we use the new alkane buffer. The FWHN is much narrower. However, if we apply the same process on there, actually we get an even worse alkane. So the problem isn't solved. It even going to the even worse direction. So how do we solve this problem? So we need to know what's the problem first. So for aluminum nitride, aluminum gallium nitride, there's an important mechanism called the self-vacancy compensation. Because while the band gap is wide, the formation energy of those point deep also enhanced. So that will make the doping difficult. While you're trying to dope silicon for the anti-doping a lot of vacancy forms simultaneously to compensate the undoping, so you will never really get a high doping. So if you get a knee point between the silicon dopant concentration and the real carrier concentration, there's a high point. And as the composition of aluminum increase, this multimole point decrease significantly. So now you cannot grow really alkane with aluminum percent more than 70% and achieve a high carrier concentration simultaneously. And another problem is that aluminum gallium nitride is fat compared to the seed provided from aluminum nitride. So it will feel the compressed. So what happens if the epithelial layer is feel compressed? First, the dislocation will be bent to release the strength. Second, if there is no dislocation, we can create some discretion from nowhere. So the fretting dislocation might be injected from the surface. And the third, if this is still not good enough, anything could happen. So someday will be some macroscopic defect cluster happened during the growth. So here is the response hierarchy to the compressive strength. So for N-alkane growing on the aluminum nitride template, at the beginning, the surface will be undulating. And the second, the TD will be bent. And the third, the TD might nucleate from the top. And the final, you will get all kinds of defects together. So at the beginning, we have a poor aluminum nitride template. So it might be, we have a TD bending to solve all the problem. But however, if we have a really nice template, we will skip the first step. We still get a lot of aluminum dislocation in the end. So it looks like a dead wall. So, okay, because I'm running out of time. So this is the design trilemma. You cannot really obtain a low TDD and sufficient gallium composition for good contact, and decent thickness for the series sense simultaneously. And this is even worse if you have an even lower TDD. That's not gonna happen. So what's the breakthrough we done to solve this trilemma? So there's a very interesting phenomena called the surface medial dislocation tilt. So when a vacancy encounter the dislocation, and it will be aggregating because the compressive, this is local compressive for dislocation, and it will attract the locally tensile vacancy and eventually release the strength while it grows. So you will see if we can dope the aluminum nitride with the silicon, and we can eventually release the compressed strength in the end. So this is about the model, how we verify this model. Anyway, it's very inconsistent with our model. We found that the more dislocation and the higher regrowth thickness, we can eventually get rid of those dislocation from the epi. So, and we also verify the model with TEN. The theoretically predicted the dislocation tilt angle is the same with the TEN observation. So it's actually a very good model. So now after with the high silicon doping aluminum nitride, the strength is gradually released from in the beginning. So we see we finally successfully transfer the good aluminum nitride property to the outgain. So okay, I'm gonna skip this part. So a little bit over detail. All right, so now we can grow a high quality N outgain on that because we relax the strength in the aluminum nitride. Then we successfully to boost the EQE up to 3-folds by the time in 2020. And after 3 years, the industry even boost the efficiency 3 times again. So it's a much brighter UV-COD compared to now. So now it's a little bit dangerous. You shouldn't shine it on yourself. All right. So what we can do in the future, because now we are not a grower anymore. So those aluminum nitride actually is a pretty good stuff for the meta lens because it have a high refract index in the UV region, while others is absorbing. So we have already demonstrated that we can make this planar buffer making a lens, and so these are all experimental data. And we can even shoot only focus one circular polarized incidence with such film, and it will be, because it's our recent work, it will be published probably in the next few months. All right, so thank you for attention, and I will be taking your question.
Thank you for your good talk. So, questions?
Actually, my question is just a general question, not really, because I have always been curious about those kind of material with a larger band gap. So with a large band gap, that quite, as you this in the last few and the tape slides, quite a series of material with large band gap. So for this one, what are the quantum yield? Because when LED or the LED or laser, the optical excitation, the emission efficiency are very important. So for these materials, and what are the general, what are the quantum yield?
Okay, so that's a very good question. That's like a number we are competing with a different group. So I think I will just go to the very starting page. All right. So this depends on the wavelengths you're interested. And it's now for the UVC LED, because UVC is pretty wide. It ranges from 200 to the 280. For the 200 LED AP, the internal, because this is all external efficiency plot. For the internal quantum efficiency, we all believe it's now between 40 and 50. 40% to 50% for the internal quantum efficiency. But we have a great issue in the light attraction because the photon energy too high. It's very difficult to get a transparent contact to extract light out of the chip. So according to some low temperature PL measurement to measure its decay lifetime, and we believe that the best of the reported number is about 50% of the internal quantum efficiency. But the final EQE is only still less than 10%. That means like only the light extraction efficiency is less than 20%. So it still makes the overall number looks a little bit miserable.
But that's still very good, 40 to 50%. Okay.
Yeah.
Okay,
But
thank you.
that's some kind of champion data. People still skeptic about that because if you want to achieve a 50%, okay, there's a theoretical plot here. If you want to achieve an internal quantum of 50%, the fretting dislocation should be almost like a 1E8 per centimeter square. That's actually pretty difficult still even with the new technology. Yeah.
So that means associated with the defect, right? That was another term, the dislocations.
Both
somehow.
dislocation and point defect.
Yeah.
Or point defect like vacancy, oxygen impurity,
Okay.
and free aluminum impurity. So like all the library that.
So you mean mainly the defect state and the introduce and the gap state. So
yeah, there's something
with
will be deficit in the middle band gap, so the energy will be lost during these middle levels.
okay.
Yeah.
Okay, thank you very much.
Some more questions? Professor, just one question about also regarding the same question of Professor made. It's about the effect with this kind of quantum efficiency with the temperature, how it works in this case, how it's the behavior of the quantum efficiency with dependence of the temperature.
Oh, so actually because the outgain is a very wide band and strong stuff, so usually we didn't really count the temperature as because it's a wide band gap, so the quantum wave is very deep.
Okay.
So it's actually rather resistant to the temperature because usually we don't raise the quantum the LED to 100 or something. So normal operation shouldn't be a big issue to the efficiency, but it's a big issue to the reliability. That will affect like how the efficiency will decay after 11 hours, 10 hours, or 1,000 hours. But at the moment you just lit it up, the temperature should be rather. It's not the biggest deal because the efficiency already pretty bad. So you don't care about the temperature at the current stage.
Okay. So thank you again for your nice presentation.
Thank you very much.
So now I ask you for the presentation for the Professor Kentaro Nishida, photothermal scattering control in silicon nanostructures. So thank you, Professor, for accepting the invitation.
Thank you very much for introduction. So I start my presentation. So my name is Kentaro Nishida from National Taiwan University. I modified title a little bit. Photothermal scattering control in silicon nanostructures for super resolution optical microscopy. So let me start the talk from the optical microscope. So optical microscope is, as you know, that it has advantage or non-contact and non-invasive observation, and also we can observe inside of the material because light penetrate into the material. So because of this advantage, so there's many applications such as biomedical study, also material inspection. However, the optical microscope, the spatial resolution is not very good, because if we focus the light by using very high NA objective lens, but we cannot make infinitely small spot. But it has the due to the wave nature of the light, it has has a finite size which is almost same. Even highest, it's smallest, it's almost about half of the wavelengths. So in laser scanning microscope, we use this kind of finite size of the spot to scan the sample. So actually, the image is little spread due to the size of the focus spots, and we cannot distinguish this detailed structure. So this is a limit of spatial resolution. So to overcome this problem of limit of spatial resolution, there are some technique called the super resolution microscope. There's two representative technique. One is called PALM and STET microscope, which get Nobel Prize in 2014. So in case of PALM, they use the photo-activated fluorescence molecule to randomly activate the fluorescence in the different time points. And they record the position of the fluorescence level, and finally reconstruct a very detailed distribution of fluorescence molecule. On the other hand, STET microscope use the donut-shaped pattern to induce the stimulated emission of the fluorescence molecule to overlap this conventional laser scanning spot. As a result, we can suppress the fluorescence at the edge of the focus spot along this donut pattern, and the effective size of the focus spot reduced, so we can improve spatial resolution. So this technique is great breakthrough. However, the drawback is to apply this to technology, we need a fluorescence labeling, so it's very difficult to apply for material observation. So our group research is that we achieved the label-free super resolution imaging of silicon nanostructure. So this is one example of our results. So when we observe this very small 100 nanometer silicon nanoblock on the conventional optical microscope, it's spread image. This is the original size of silicon. But if we apply our super resolution technique, we can improve spatial resolution. So the image size is close to the original size of the sample. So I explain how we achieve this technique. So we utilize the optical response, special optical response of silicon nanostructure, which is term of the Mie resonance. So Mie resonance is shown in this, the mechanism is shown in this schematic. So we illuminate the silicon nanoparticle, which is almost same size with the wavelengths of incident light. It shows cause the resonance between the incident light electrical field and also polarization of this the polarization of the silicon nanoparticle in similar term of plasmon resonance, then localized plasmon resonance. Then it's scattered its emitter scattering, right? We call this is Mie scattering, and there are several type. One is another is a magnetic dipole. It's the resonance mode. It's cause the circulating electrical dipole mode and the linear magnetic field. Anyway, because of this resonance mode, because of this resonance mode, if we measure scattering spectrum of silicon nanoparticle, which size is 150 nanometer, and this spectra, you can see that it shows a sharp peak at the specific wavelengths. So this is the point. Our group find this Mie scattering show the intensity, show the saturation effect by thermal effect. So we eliminate this silicon nanostructure by single wavelength excitation light like a laser. So then the temperature of the silicon increased by photothermal effect. Then the refractive index of silicon changed by the thermo-optic effect. So as a result, this scattering spectra show the redshift as the temperature increase. So actually, the scattering peak go away from the excitation intensity, and the scattering efficiency start decrease. So what happened? So here's the relation between excitation intensity and the scattering intensity. So if we increase the intensity like this, the temperature of the particle increase, the scattering intensity does not follow linear, but show the slight saturation effects. So actually, Mie scattering saturate at the high excitation intensity. So why saturation matter? actually saturation is important to break the resolution limit in optical microscope. So if we go back again, laser scanning microscope, as the center of focus spot has a high excitation intensity compared to the edge of focus spots. As a result, that only the center of focus spot, the saturation effect of scattering happen, but the edge does not show the saturation. So if we scan the sample in this situation, like this, then if we can detect only this saturated signal, that means we can detect only this center of focus spot signal, so we can improve the spatial resolution compared with the conventional technique which detect all of region of the signal. So this is a trick. So how we detect only saturated signal? So we apply the temporarily modulated excitation intensity to the sample. So temporarily modulated excitation intensity, the excitation intensity changes depending on time at a single frequency. So as a result, if the at the signal center of focus spot shows saturation, that means this waveform shows the distortion compared with original waveform. At the edge of focus spot, the signal linearly follows, so the distortion never happens. So if we consider in the frequency domain, this distortion produces this high harmonic signal. So if we detect this harmonic signal by using lock amplifier, we can detect the signal of the center of focus spot. We can improve the spatial resolution. So here is the experimental result of super resolution silicon imaging by using saturated scattering. So we measure the 110 nanometer silicon nanoblock. So in conventional microscope, this is 110 nanometer, but the image spread, it's very big, the 290 nanometer resolution is not good. But if we detect the harmonic signal like this, we can reduce the spread of the image. That means improve on spatial resolution. And if we detect high order signal, the spread become more small, and actually image size become very close to the original size of the sample. This is one demonstration. So we also achieve the super resolution with different mechanism. The use of the superlinear signal by using a superlinear signal. So what is a superlinear signal? Superlinear signal is if we plot the relation between excitation intensity and the emission intensity, it does not show the follow linear trend, but it's increase the high order of the nonlinearity over this linear trend. It's like opposite of the saturation. So actually, excitation emission intensity follow in this figure the p order of the excitation intensity. So we call this trend as a superlinear intensity increase. So if the signal in laser scanning microscope, we scan the sample with the focus spot. This focus spot intensity distribution is approximated by this Gaussian distribution. Then if the emission intensity follow p order of the excitation intensity, we can input this excitation intensity to here, and we can transform like this. That means as a result, the signal response of a distribution of the signal response reduce the root p times smaller. That means the spread of the image decrease. So if we increase higher order mode of the higher order of nonlinearity, the spread of image decrease like this. So we can achieve the very high resolution. So the point is how we how we induce this kind of steep superlinear signal. So to achieve this, we focus the phenomenon called the optical bistability, which is the key to achieve the steep nonlinear scattering. So optical bistability is already classically known. So its induced is a combination of the resonator cavity and the resonator cavity filled with the nonlinear medium, which refractive index changes depending on the intensity of the field. So when we illuminate the light into this resonator cavity, the intensity field of the intensity of the cavity change the refractive index, and the refractive index change the intensity of the field intensity of the inside of the cavity. So there's a very complex iterative feedback relation. So as a result, the relationship between input intensity and output intensity show this kind of S-shaped curve, especially this region called the bistable region, indicated by this green color, shows that for one input intensity, there's two stable states. So that means if we consider to increase the input intensity from 0 to high over this bistable region, then there's a steep jump of the input intensity in the process of the transition of the state from here to here. So this is the key to achieve very steep superlinear signal. However, to achieve this bistability, this very high Q, very narrow sharp high Q factor, which means narrow resonance peak or very large N2 value, we require this condition. Unfortunately, in case of silicon, the N2 value is quite low. So conventionally, people achieve optical bistability using this silicon ring resonator, which size is about 100 micrometer, but the Q factor is quite high, over 1,000 or 1 million. Then, but on the other hand, in case of nanosilicon, the Q factor is very low, so because size is low, so optical bistability has not been reported yet. But as I explained in the beginning, the use of thermal effect in mid-resonance nanosilicon allows us to boost the N2 value by using photothermal heating under the high refractive index change by thermo-optic effect. So according to our investigation, at the maximum condition, the N2 value, effective N2 value of this in photothermal refractive index change reached 0.1, so which is much few order higher than the N2 value of silicon. So that's why we expect to see the optical bistability in case of the silicon nanoparticle by using photothermal effect. So let me explain the principle of the photothermal effect optical bistability in silicon nanostructure demonstrated by our study. So we assume we illuminate a silicon nanoparticle with single wavelength excitation light, which is like a laser. And this excitation wavelength locates the red side of the absorption peak. Then, by increase the excitation intensity, the temperature of the silicon increase. That means refractive index change and absorption peak show the red shift like this. So, as a result, this peak across this excitation wavelengths. That means if we plot the relation between temperature and absorption cross-section at this excitation wavelengths, it's follow this one peak graph following this absorption. How much time I have? 5 minutes? 3 minutes, okay. And yes, and the one peak graph following this absorption spectra. On the other hand, if we consider the heat diffusion is just proportional to the temperature of the silicon following this Poisson equation. So if we plot the diffusion graph on this plot, we can show this kind of straight line. So then if we consider the thermal equivalent point, which is absorption should be equal to diffusion. So then we can see, that means the overlap point of this three graph. So overlap point three graph. So this point becomes thermal equivalent point. So to evaluate the potential stability of this thermal equivalent point, we calculate the potential by differentiating the total heat flux, which absorption minus diffusion by temperature. So as a result, this yellow point indicated by this yellow dot locates the dip of the potential peak. On the other hand, this yellow point locates the peak of the potential, so it becomes unstable. So there's two stable points. That means we expect to see the bistable phenomenon. So here is the experimental result of the to demonstrate sharp superlinear scattering from silicon nanoparticle by optical bistability. So we fabricate 150 nanometer size of amorphous silicon, and which the Q factor is only 4.4, and we limit 785 nanometer, which locates left side of the peak. And here's the relationship between excitation and scattering intensity, as shown in this blue curve. If we increase the excitation intensity, it shows very steep jump, which reach order of 180 in log-log plot. On the other hand, interestingly, if we decrease the excitation intensity from here to here, it does not show same path, but it shows the hysteresis effect. This is also one the evidence of optical bistability. And by using this optical bistability, we demonstrate super resolution imaging. So if I fabricate this kind of the closely relocated silicon nanostructure, and if we observe a conventional microscope, we cannot distinguish this structure. But if we increase the excitation intensity, the bistability happens, superlinear scattering happens, we can improve the spatial resolution. So this is a summary of my talk. So, and this research is conducted with many international collaborators, so I thanks to them. Thank you very much.
Professor Nishida, questions?
Yeah, thanks for your presentation. It's really interesting work. And I'm wondering why you choose the silicon nanoparticles and whether this the label-free technology could be used for other kind of the materials, like the metal or something else. So I'm not sure why. What's the specific reason why you choose the silicon nanomaterials? Yeah.
Thank you very much. So very good point. Actually, the reason use silicon is for application. We consider finally we try to observe want to observe IC chip, like we use smartphone. The inside of the IC chip, they are made of the silicon. It's very small structure of silicon. So currently, people use electron microscope to observe this kind of structure because resolution of the optical microscope very bad. But our hope is finally, if we use our technique, we can observe this kind of very few nanometer structure by optical microscope by improve the spatial resolution. On the other hand, in case of metallic particle like gold, we find it's also show the saturation effect by using plasmon resonance, because if we eliminate a nanoparticle, it also increase the temperature, and temperature increase cause the damping of the oscillation of the electron. The electron cannot move very easily. So scattering does also show the saturation like this. So we can observe the gold, but we stop the research because I cannot come up with good application.
Okay, thank you.
Some more questions? I have a question. Professor, I saw your result and you are speaking about the variation of the refractive index with the temperature. So in this case, this is the DNDT. So the DNDT in this case of silica, in this case, the DNDT is positive, right? Yes, because the DNDT is in this case is positive. And so, now, for example, if you try to use, for example, in this case, one material with a DNDT more higher than silicon material, it should be, this result could be much more intense in this case, no?
Yeah, you are right. Exactly. Yeah, exactly. So because yes, exactly. As I explained in the beginning, this saturation effect comes from this spectral refractive index change. Spectral shift is caused by this refractive index. If this refractive index is very high, the spectral shift is also very high. That means this decrease of the scattering cross-section at this excitation wavelength also become very large. So we can see very intense saturation.
Okay, and in case, for example, if you use, for example, a lower wavelength, when the refractive index is more intense, and did you try to do that with a different wavelength, for example, instead of just in the yellow, but going, for example, for the blue or?
I have not tried yet, because actually this sharp peak, caused by this localized electrical field inside of the wave. This has electrical field, and this resonant with this polarization, oscillation. So if the wavelengths become shorter, the loss become large. So electron become very difficult to move inside of the cavity. So this peak become broader.
Okay.
That's also cause another problem. But thank you. I think this is also a good point.
Okay. So thank you again for your nice presentation and very nice idea. Thank you again.
Hello? Hello, can you hear me?
Just a minute, Professor. Just 1 second.
Sorry, Professor. Please open your webcam. Thank you.
My video camera?
Yes, now you are seeing.
Okay now?
Yeah, yes.
Okay.
If you can bend your camera just a little bit below to see your face, because you are just seeing your middle of your face.
Is it okay now?
It's better. It's better. Okay. So, thank you, Professor Zembal, to accept the invitation. And his talk is about the melt recrystallization process for silica coat perovskite nanocrystals.
Okay, good afternoon, everyone. My name is Zheng Bao from Changzhou University. My topic is about the melt recrystallization process for the silica-coated perovskite nanocrystals. I will first discuss the motivation of my research and talk about the mechanism of the sintering process and the application for the free primarily color-emitted perovskite concept and the conclusions and future perspective. First, it's well known that perovskite nanocrystals is a famous material in the past decade due to its excellent luminescent properties. For example, it has the quite narrow emission band, the high quantum yield, and it's very easy to tune the emission color that all covers the visible range. But the main disadvantage of this material is the poor stability, and it limited its further application and the usage. So to solve this problem, the researchers concentrate on solving the stability of perovskite nanocrystals in recent years. The main solution to deal with it is do the materials coating. And the coating can be separated in these main ways, such as use the chemical coating by the TMOS or TILs, use the mesoporous material to cover the perovskite nanocrystals, to embed the perovskite nanocrystals in glasses, or use the ALD to do the metal oxide coating of the perovskite nanocrystals. Well, within these methods, if we want to keep the material-coated perovskite still remain the nano size, maybe mesoporous material should be the most easy choice to obtain it. The normal way to do this is just mix the perovskite solution with mesoporo-silica powders, and the perovskite solution will be absorbed into the pores of the silica and made it dry. But the silica didn't well cover the perovskite nanocrystals, so the stability enhancement is still not so excellent. So if we sinter this composite and at a high temperature, the mesopore silica will collapse. So it will obtain the dense coated silica on the perovskite nanocrystals. There have some researches on this topic, but the main way of this main way to realize this idea is dissolve the cesium bromide and lead bromide in the water as a solution. Then absorb this solution into the mesopore silica. After sintering, it will be the silica-coated perovskite. But in this way, most reports are only limited on the green emission samples that the silica-coated cesium lead bromide 3, but it's hard to get the red and blue composites. The main point that we cannot read this is first, the lead iodide is easy to be oxidized when it's dissolved in the water. And another is the cesium lead halide perovskite will melt and decompose over about 560 degrees C. So we need to find out the real sintering process, the detailed sintering process of this coating method. Then we can obtain the red and the blue composite. First, we did the TG and DTA measurement of the mesopore silica. As shown in the DTA curve, it started to have energy flow from about 475 to 760. It means during this temperature of heating range, the mesopore silica started to quickly collapse, and this phenomenon will make the silica well coated the perovskite. Then we did the TG and DSC measurement on 3 kinds of the precursors as the green, blue, and red perovskite precursors. We all can find the small flow peak on the DSC curves of these precursors at about 540, 560, and 450 degrees C. And this is corresponding to the melting point of the perovskite crystals. And we can see, start from this temperature, all the perovskite precursors started to show the weight loss. That means it started to decompose. Then we did in situ XRD measurement of the mixture of cesium halide, cesium bromide, lead bromide, and mesopore silica. When we sinter the mixture of these compounds, it first show phase transfer from the room temperature to 400 degrees C. That we can see it mainly show a mixture phase of orthorhombic cesium lead bromide 3 perovskite and cesium lead bromide 1, 2, 5 this composite. And when the temperature keeps up to from 400 up to 540 degrees C, the mixture phase started to turn to only one phase of orthorhombic cesium lead bromide 3 perovskite. And when it's over 540, that means we see the melting point in the DSC curve. The XRD pattern shows the amorphous phase of this of these mixture compounds, and the amorphous phase keeps during the temperature holding at 600, and the first period of the cooling process from 600 to 200 degrees C. After 200 degrees C, after the temperature lower than 200 degrees C, the perovskite started to turn to the cubic 113 phases that our target phase. From these XRD data, we can derive this mechanism of the sintering process. That the first period is started to the precursor of the sedum halide and lead halide started to show the mixture of these two kind of peroxide phase, and then turn to only the orthorhombic sedum lead bromide free phases. And in these two periods, the mesoporo did not show any changes. And when it comes to the temperature over the melting point of the perovskite, the crystal started to turn to the liquid phase, and it will be fulfilled in the porous of the silicas. And during the temperature holding process, the silica and the mesoporous silica started to collapse, and the pores are closed, and the liquid phase of the perovskite are well coated into the closed silica pores. During the cooling down process, the perovskite started to recrystallization, and then finally all covered in the silica particles. And we call this process as melt recrystallization process. Then we attempted to use this process to try to synthesize the three primary color emitted perovskite composite that coated by silica. The process like this, first we just mixed the sedum halide and the corresponding lead halide together, and use the mercer furnace to sinter first, at about 400 degrees to get the perovskite precursor crystals. Then we mixed these precursor with the mesoporous silica nanoparticles together, and set into the tube furnace to sinter again. In this section, the prepared perovskite crystal will first melt and then recrystallization in the holes of the mesoporous silica, and finally get our well-coated silica. The target silica-coated perovskite nanocrystals. After wash and dry, it will be the final samples. This process avoid using the water in the first step of mixing sedum halide and lead halide that can be easy to get the red and blue samples. From our tuning process, we found that from about 550 degrees C to 700 degrees C, we can all get the blue, green, and red perovskite composite. Then when we check the PL properties of the three sets of samples to find out the best sintering situation. As we can see from the PL spectrum, all these sets of samples show a red shift when the synchrone temperature enhanced, and the full white at half maximum have a trend of getting narrower. Finally, we checked the PLQY of these samples, and we found that at about 650, all these samples can get a high a high QI that we select 655 as the best situation. Then we checked the decay curve of the samples. From the decay result, we found that at 650, the decay curve more like to be linear, and that means there will be less trial and by exciton process in the recombination process. So and also this result is corresponding to the PLQY result. Then we checked the PM of these three samples to see if the perovskites are well coated by the silicon. From the first three images, we can see that both the RGB samples have a particle size of about 200 to 500 nanometers, and it seems they are aggregated together. Within each small particles, we can find many dark dots inside it. And from the high resolution image, we can identify that these dark dots are the 113 phase of perovskite with different components. And this proves that the success of our experimental design. Then we checked the thermal stability of the samples, where we tested 15 loops of the RGB samples, and they show about 99%, 90%, and about 82% of the original intensity after the thermal loop tests. Finally, we fabricated these three samples on the UV LED chips to gain the white LED. These images show the single color emitting LED. When these three samples mixed it together as a white LED on UV chip, it shows a large color gamut of about 119% of NTSC standard in the CIE image. Then about the stability, we use the single color LED to test the stability, and it shows after a long period working status test for up to 500 hours. The RGB LEDs shows the 83%, 82%, and 96% of the origin intensity. That means it can keep the working for a long period. Compared to the non-coated RGB samples, they can only hold for several hours. It means the success of this melting recrystallization process for the silica-coated free primary color emitted perovskite composite. Also, from the CIEX and the CIEY coordinate curve, they all keep very stable and do not show large color shift in the CIE pattern. As a conclusion, in our research, we found that melt recrystallization process is the mechanism of the sintering metal halide and mesoporosilicon for the perovskite composite. And with this process, we can easily get the three primarily color emitted perovskite composite. For the future perspectives, we are attempting to synthesize the silica-coated multidimensional perovskite composite to further enhance their stability. Okay, that's all my report. Thanks for your attention.
So thank you, Professor Zimbao. Some questions?
Thank you for the talk. Can you hear me?
Yeah.
Yeah, I have a short question about the results. So in page 12, I think 12, you show the redshift of the spectra depending on temperature.
This one?
Yeah. And interestingly, the from 650 green curve and 700 red curve, the spectral shift look
You
like
mean
stop.
the redshift of the PL curve?
Sorry, say again.
Sorry, which one do you mean?
Yeah, for example, figure A,
A, B, and C, yeah.
inset figure. Then the temperature increase, then spectra show the redshift, right?
Yeah.
Then from 650 to 700, the spectra shift stop, right?
Sorry, I can't catch the last sentence.
Okay, inset of the figure A, inset figure of figure A, small figure of figure A, there's four curve, right? Purple, blue, orange, green, and red.
Yeah.
And the
The blue,
temperature.
green, and red.
Yeah, temperature increase from purple to blue, right?
Meaning the blue?
Temperature change from purple to temperature increase from purple to blue, right?
You mean temperature increase with what?
With
Sorry, I can't hear very clear.
oh.
I think you want to know about the figure A. Figure A, no?
Yeah,
figure A. No, below.
Yeah?
Yes, this one?
Yes, this figure.
This one?
Yes, this one. And for example, if we see 550.
Yeah, 550?
And 600.
600, yeah.
It shows the red shift, right?
Yeah, it shows the red shift,
Yeah.
yeah, right.
But from green to red, 650.
You mean from green to red? Yeah.
No shift, so I want to ask why.
Oh, okay, I know your question. It shows from green to red like this. 615 to 700. Also, it shows in the red sample. It shows the little blue shift that not the same trend. We think it should be even at the quite high temperature that we mentioned the TG and DS curve. The perovskite started to decompose, so that the concentration ratio of the perovskite will decrease. That caused the smaller particle size of the perovskite nanocrystals. That caused the little blue shift at the higher temperature.
So, thank you. More questions? No? Professor Bao, I have one question. If you try to make because you show several LEDs with different colors at the end of your presentation. Did you try to make a white light LEDs using this mixture of these perovskites?
You mean the LED mixed with the mixture of the
yes.
sample?
Yes.
We did that and show the CI of the obtained white LED.
Yes. Did you succeed to do that?
What?
because you made different LEDs with different colors.
Yeah, we did two kinds. We did the different colors, and we also did the mixture of three samples to get the white color. Sorry, I forgot to show the picture of the white LED. Here.
Okay.
Okay, because CIE should use the white color one to show it the color come out. But
Okay.
when we do the stability of each color, we use a separate one.
Okay. Yeah, no, this is just a question about that. So thank you for your presentation, Professor.
Oh, thank you.
Session will finish because Professor Jensen will now come.
Okay. So unfortunately, the section will be finished because Professor Zheng Shen will not be present to his talk. So thank you for your attention, and I hope you enjoy the coffee now.
哦，真的、啊？
对对对。对，所以到时候会是，都要用麦克风才听得到那个。
就他们才听得到我的声音，要用麦克风了。
对对对对对。
这只或那只都可以。
对对对。
好。
老师好，是 chairman 吗？
对。
等一下都是线上报告。
所以时间到我就开始讲。他们反正会按照顺序上来嘛，哈。
对对，我们会调那个谁上来，然后谁才会报告。
他们不会看到我们这边的画面。
不会。
看不到。
对，但是听得到声音。
看得到。
看到吗？
老师看得到我们，老师你对着镜头，他看得到我们。
哦，这样子啊。
对对对。
所以我还是要表演一下，要对着镜头讲。OK， 好。
老师你看着镜头，你可以侧身啊。然后我们的摄影镜头会拍着你，然后他们看得到我们，也听得到我们的声音。
好。
对。
好。
所以老师你可以站在那个投影幕的两侧，我们会去拍你，那您讲话麦克风讲话，他们都听得到，这样。
好。那我还第一次这样主持这个线上的会 ，speaker 通通不在现场，都在线上。
对。
对呀。 already 4 p.m. But we still have some technical problems, so we need to wait for a few more minutes to start the section. By the time, let me introduce myself first. I'm Chin-T Chen, the chairman of this section. I'm from Academia Sinica. So in this section, we'll have 5 invited speakers. So are we ready? Okay. Our technicians say not ready yet. Okay, fine. Okay, it's ready. Okay, let me start it. Our first speaker in this section is Professor Fan Wang. Professor Wang is from City University of Hong Kong. And let's start it. Professor Wang, you can start your speech now.
Okay, thank you, Professor Chen, for a kind introduction. And also, I want to thank the organizer committee for inviting me to give this talk. Today, I'm going to share our recent work on doping lanthanide and transition metal ions into different host materials to obtain some interesting optical properties. And here is a summary of the research activity in my group. Like many of you, I work on semiconducting luminescent materials and also doped organic crystals. And particularly we are interested in doped inorganic crystals because, as shown here, so we can dope some particular ions into an insulator, non-luminescent materials, and we can modify the energy level structures inside of the crystals, and so that we can achieve highly tunable emissions. And also, we also interested in technological application of the materials in such as photonic memory, and bioimaging, and information security. So we are so interested in doped inorganic crystals because if you look at a theoretical table of elements, you will see there are many elements available for doping, and then we can dope different ions into a same crystal so that we can create a highly tunable emissions by using a single host materials. And on the other hand, so we can also dope same ions or same set of ions into different crystal structures or different crystal materials. And in that case, we can also obtain highly different, very different optical properties. So that's the motivation. We are so interested in synthesis of different types of inorganic materials and dope lanthanide and sometimes transition metal ions into the host materials to achieve some unique optical emission properties. And today I'm going to share our work in 3 categories. First is we use, I will show you how can we use a causal nanostructure to realize emission enhancement and optical tuning. And also, we are talking about using some host materials with a unique crystal structure, and particularly they can undergo some phase transformation in response to external stimuli, such as thermal stimuli and water stimuli. In that case, the materials may change their phase structure, and as a result, we can realize some stimuli responsive luminescence properties. And lastly, I'm going to share with you our recent efforts in doping semiconducting house materials so that we can achieve optical emission, tunable optical emission by excitation such as mechanical force and electrical field other than light excitation. Okay, so let's start with the first part, luminescence enhancement and training by causal nanostructural engineering. And we did this part of work because we want to solve the problem of luminescence quenching in doped inorganic crystals. So typically, when we prepare, when we design and doped inorganic crystals, we want to dope as many as ions into the host materials because without dopant, so we can observe no optical absorption and emission. So when we increase the doping concentration, typically we can expect an increase in the light absorption, and as a consequence, as more light can be released as a photo emission. But the problem is that if you increase the doping concentration, so there will be a strong interaction, energy exchange interaction between the dopant and ions that will lead to a concentration quenching. So usually we will have an optimum doping concentration below, for most of the crystal is below 20%, 20 more percent. So in order to enhance emission intensity by mitigating this concentration effect, so we come up with the idea of using a causal structure because so the energy transfer between the doped ions typically occurs within the nanometer scale. If you look at the size of nanocrystals, nanoparticles, the size is also in the nanometer scale, at the nanometer length scale, so that if you can synthesize a causal structure and confine the doped ions into different layers of the causal structure, so that we can control the spatial separation, distance between different ions, so that we can regulate their energy exchange interaction, and as a result, we will be able to control their energy exchange interactions on the nanometer scale. So actually, we did a serious work in this causal structure. So here, I just want to use some three representative work to summarize the importance of the causal design. And first one is we use an inert core and active shell and inert outermost shell. Causal shell structure, we dope the luminescent ions into the inner shell layer. In this way, we can confine energy transfer in the inner shell layer. And due to the suppression of energy migration, long distance energy migration, because the doped ions is totally confined in a very small area, small region in the nanoparticle. So the energy migration induced concentration quenching can be minimized, so that you can dope very high concentration up to 99% ytterbium together with 1%, 1 more percent thulium. So we can realize very strong off conversion emission by 80 nanometer excitation and with a very large anti-Stokes shift emission at deep UV at 290 nanometers. And similarly, you can use the causal structure to dope a very high concentration of erbium into a causal nano structure. And again, we can minimize the energy migration induced concentration quenching. And on the other hand, we also devise a waveguide assisting the excitation scale so that we can maximize the excitation efficiency. and so that we can also avoid the cross-relaxation induced concentration quenching. And as a result, we can realize 1.5 micrometer excitation and deep UV emission. Again, a very large anti-Stokes shift. And recently, we combined several doping ions. As you can see, we use a color shell structure, multi-layer structure, and we can dope a site of lanthanide ions at high concentrations. And in this way, we can realize the tandem up-conversion process. And we have a two up-conversion process connected together. And for example, here we use erbium-based up-conversion to absorb 1.5 micrometer excitation, and then transfer the energy to the core layer and to realize a deep UV emission from a thulium. And then we can achieve the super large, ultra large anti-Stokes shift emission, 1.5 nanometer excitation, and 290 nanometer up-conversion emission. Okay, so and in a short summary, so here by using a color shell structure, we can dope unusually high concentration and unusual combination of dopant ions to realize a very strong up-conversion and a very large anti-Stokes shift, and through this color shell structure engineering. And if you, in all these cases, if you homogeneously dope the ions into into the host lattice without using the color shell protection, without using color shell separation, and the emission will be largely quenched. Okay. And in addition to enhance and tune the emission color, and we can also integrate multiple emission processes into a single particle level. For example, using this multi-shell structure, we can design conventionally non-80s excited blue up conversion in the core level, and then we use inner spacing layer to prevent its interaction with the shell layers, and then we can construct another 808 excited up conversion process in the outer shell layers, and then these two up conversion process is mutually independent. And by switching the excitation wavelengths, so we can realize dynamically tunable up conversion emissions, and we can dynamically change the color emission color from blue to green by changing the excitation wavelengths. Okay, but using color shell also is very effective to change the emission intensity and color. The problem is that so in some cases, if you wanted to grow a color shell with a much different with a distinctly different composition, you may suffer from the problem of isotropic anisotropic shell growth, and also the synthesis process is sometimes takes a very long time, so it's not very convenient for some particular applications. That's the reason we recently also shifted our research interest to a crystal structure, the crystal materials, inorganic crystals with a unique crystal structure, such as this zero-dimensional Ropscat structure, and this structure is this set of host is unique for luminescence applications, just like the color shell structure. And in this zero-dimensional crystal structure, we have many polyhedral luminescent units, and they have a large separation in space, just like the color shell structure. And in different shell layers, they are separate. They can separate the dopant ions, and when we dope luminescent ions into this polyhedral unit, and they will be spatially separated by this unique crystal structure, and similar to the color shell shells, multi-color shell structure actually here. And we realize excitation wavelengths dependent on luminescence, and the zero-dimensional Ropscat structure can also offer this excitation wavelengths dependent emission color, just because in this kind of materials, and we will have a if you dope such as antimony into this zirconium based host, and you will create two types of luminescent centers. One is a zirconium-based polyhedron, and the other is a antimony-based polyhedron. And because they are large, their separation is large in space, so their emission properties is essentially independent. Okay, so we can selectively excite the zirconium-based blue emission or antimony-based orange emission, just like we selectively excite the blue up conversion and the green up conversion in these multi-core shell structures. But using a zero-dimensional peroxide structure, so the synthesis is much easier. You do not bother to use a layer by layer synthesis to grow this multi-layered structure. Instead, you can even use a solid state reaction, and it's very convenient. Can be used for mass production, and also it's very cost effective. Okay, so this is why we are so interested in the zero-dimensional perovskite structure as well. And this is our first attempt to synthesize this zero-dimensional structure. And in this study, we use zirconium-based host materials. And although we realized that this excitation wavelength-dependent emission, but this this host is not very successful for doping lanthanide ions. So later on, we also synthesized turbine-based zero-dimensional perovskite structure. And in this case, we can easily realize lanthanide doping, such as the European doping, and then similar to the previous case, we can realize excitation wavelength-dependent green and red emissions, just due to the two different luminescent centers. And more interestingly, if you expose the crystals in ambient air, or just add some water into the sample, and you can observe a quick color change from green to white. Even you use a consistent 377 nanometer, and this just because the water treatment induced phase transformation from the zero-dimensional structure to a one-dimensional structure. And as a result, so in the zero-dimensional structure, there is no energy transfer between TV and EU. After phase transformation, there is a collapse of the crystal structure, and there is a substantial decrease in the TB and EU separation. And then, as a result, you can expect a strong energy transfer from the TB to EU. That's a reason. And this water responsive luminescence color change. Okay, and in this case, you can use a constant UV excitation. You do not need to change the emission color. And I think the interesting thing here is that so for the rare earth-based crystal, we can realize the different types of the rare earth doping, such as the European doping I just mentioned. You can also dope optically inert yttrium ions, and you can control the doping concentration so that you can manipulate the energy transfer process through this doping concentration control and doping composition control. And as a result, you can realize this multicolor water responsive multicolor emission color change. So this is so far this is I think it's not possible in semiconductor-based materials to realize the multicolor change. And also, this process is very reversible. You can use heating to remove water, and the color can be restored. And you can add water again, and to induce another cycle of color change. Okay, and this can be also used for information protection. Okay, I think my time is running out of time. I have to go faster. And also, we can use RB doping to change the phase transition kinetics so that we can realize a quantitative water detection based on this water-induced color emission color change. And also we can use this phase transition to realize this sensitive thermometry based on the temperature-induced phase transformation. Now we can realize phase transition at different temperatures, and so that based on the color change, we can detect the temperature with very high sensitivity. Okay, for the multimodal luminescence, in previous examples, we all needed to use light to excite the luminescent materials. But sometimes, if you use some special materials such as the zinc sulfide, you can realize optical emission by electric field excitation or by mechanical force excitation. And this is just because of the unique semiconducting property of the zinc sulfide crystals. The problem is that the zinc sulfide can only accommodate a very limited amount of very limited types of doped ions, so that the emission color is very limited, narrow color gamut, and also very low color purity. So in order to solve this problem, I propose the two strategies. One strategy is to compose a core structure. We coat perovskite nanocrystals as an acceptor around the zinc sulfide core particles, and based on the energy transfer from the blue emitting zinc sulfide to the perovskite nanocrystals, we can fine-tune the emission color, and so that we can realize very highly tunable emission color by electric field excitation, and we can realize flexible display devices, and such as user interactive. Okay, I will skip the movie. Okay. And another strategy is we use a crystal structure similar to the zinc sulfide. We recently developed a kind of a CZOS, calcium zinc oxysulfide. It has a very similar crystal structure to zinc sulfide, and to our delight. So if we dope, because this CZOS have a calcium site, it's possible to dope Latin ions. And in this study, and although we haven't realized electric field induced emission, but we realized the mechanical excited molecular emission for the first time. Okay, from visible and near UV to near infrared. And also because it's a very similar crystal structure between the zinc sulfide and the CZOS, we also synthesize a type of a hydro structure which can realize much stronger emission than the single phase materials. And another advantage of the CZOS again, because it has a calcium side, it also has a zinc side, so it can dope many types of doped ions, so that we can realize highly tunable persistent luminescence within these single host materials. And the important thing here, and we like in the zinc sulfide, we also realize the donor acceptor emission in this host. And further, by tuning the donor acceptor emission property, we will realize the emission wavelength, continuous tuning of the persistent wavelengths for the first time in this host materials by blending the CZOS and SR, strontium zinc oxysulfide, and by control the band gap of the host materials, we can continuously tune the energy of the donor acceptor emission, so that we can realize a continuous tuning of the emission wavelengths. Okay, in addition to the CZOS, we also studied other types of materials, especially this gallium oxide. Recently, we can prepare the nanoset of gallium oxide and realize very broadband near-infrared mechanical luminescence, and which can be used as a near-infrared light source for absorption spectroscopy. Okay, I think I have no time. I will stop here. Thank you for your attention.
Okay, very good. Any question from the audience?
Thank you for a great talk, Professor. So I have one question about the self-trap excitation mechanism. So in my knowledge, the self-trap excitation mechanism requires the electron transfer from the free excitation level to self-trap excitation level. So to move the electrons from A ST level to B ST level, they have to overcome the energy barrier between them. So
Which part?
Yes. The self-trap extone, the parts, the second section.
Second section.
Yes.
You mean here?
Yeah, I'm. So in this case, the energy seems to move from the terbium to europium. Is it right?
Actually, in here, we in our opinions, energy transfer is not electron transfer. It's a more it's a kind of a freight, phosphor resonance energy transfer. It's a kind of a field interaction, not electron transfer.
Okay. Thank you very much.
No problem.
Any more question or comment? Okay, because we started a little bit late, delayed it. So, but you already used all your time. So I guess I will stop your talk here. Let me thank the speaker one more time.
Okay, thank you.
Thank you. So the next speaker is Professor Chong Gin Ma. Professor Ma. Professor Ma is from Chongqing University Post in Telecommunication.
So, you hear me?
Yes, yes.
Okay, thank you. So, many thanks and for your introduction to me. I'm Chonggen Ma from the Chongqing University of Post and Telecommunications, Chongqing, China. So, before my presentation, I would like to show my thanks and to the Professor Lin for his invitation. Secondly, I also would like to thank and to all the participants and to all students. It's a very great success. Let me about overlaying eliminated of the is outline of the my plan.
Professor Ma, let me stop a little bit because there's something wrong in your voice. Your assistant, the voice is not continuous. And sometimes it's just silent. Yeah, it's not clear. It's not clear at all.
The combination of the
yeah, your voice on and off, on and off. It's not continuous. No, still the same. Still the same.
Hear me?
老师好，我用中文跟您沟通方便吗？
您说。
老师，您在那个设定里面，您可以帮我把这个静音的部分重新开启您的声音、您的音频。然后您现在是使用耳机麦克风吗？
应该是使用。
对，那您可不可以直接把耳机麦克风变成您的那个您的笔记本，您的笔记本的上面的那个直接收音跟扩音。
我本机的是吧？
可以这样子可以。您是直接笔记本收音跟听到声音吗？麻烦您帮我直接使用笔记本。
能听到我说话吗？
可以这样子正常的。您帮我把这个您的那个
能听到吗？
投影屏帮我切出来好吗？麻烦您。您共享您的那个 PPT。OK， 我们看到了。老师，麻烦您帮我讲几句话好吗？
您能听到我说话吗？
听得到，很清楚。
顺利吗？
听很清楚，非常清楚。
很顺利。抱歉，非常 I'm sorry for all these operations.
Okay, thank you for Professor.
Okay. So, well, if you all of you listen me clearly, okay. So I will keep to giving this lecture. Okay, so first part is the motivation and the background. Then after that, and we'll demonstrate how to understand the site occupancy and the levels and the transition intensity of the 3D 3Is in the solids by using this semi-empirical crystal field insights. And then within these physics and models, and let us see how to make the first principles prediction of the structural, electronic, and optical properties of the 3D 3Is doped phosphors. And before the experimenter, we trust that such prediction can open new perspective and in AI-aided design. So finally, I should conclude will end my talk. Okay, so first part is the motivation and the background. Then there are so many these of the electronic application for 3D3Is and doped phosphors. For example, when deep red light and emitted by the chromium 3+ and containing these phosphors can be used for indoor plant factory because the energy and emitted is favorable for the plant growth. And those phosphors also are good tool for this long invasive and chemical detection because near infrared and light in the second biological window can be easily absorbed by those organic molecules in the solvents. Additional application to something organic is about this bioimaging or photodynamic and strapping because of the near infrared light and has the high penetration to the biological tissues without any autofluorescence and from the biological tissues. So the last application is related to the daily lighting. So it's quite well known for us and the quite warm red components such as from the magnet plus is needed for the development of the white LED industrial. So the question and behind of those applications arising, why 3D doped red emitting phosphors are so attractive and rather than other these counterparts such as the travelent and the dominant netted eyes or NF square type eyes. So in my opinion, and first of all, they are quite cheaper. So the second point is that their excitation and match very well with the excitation or the light emitted by the blue and ultraviolet LED chambers. And this spin forbidding the emission or transition from the 2E to the 4A2 can be observed to issue the color purity of the light that you observe. So the last point is the emission energy can be tuned from the deep red, from red to the deep red, then for various kinds of the applications. So those and advantages and triggered a lot of an investigation reference papers and in the database of the Web of Science. If we use the keywords of the chromium 3 plus and the luminescence as the keywords and for search. So, well, in January, and when we talk about something and the hotness, and definitely we will have to approach something colder for here. So, including this site occupancy of and energy levels and the transition intensity of the 3D3 eyes and in the solids. So, first of all, I would like to talk about the site occupancy from the physics perspective. So if we talk the 3D3 eyes and into the lattice constants, such as octahedrocyte, then 3D electron will definitely fully occupy the T2 orbiter in the lower energy direction. And whereas the highly lying, the EG orbiter definitely are empty. However, if the ion just goes to the tetrahedrocyte, then the case then became quite opposite. So the third 3D electron definitely will go to the highly lying and T2 G orbiters. If this T2G orbiters is quite close to the conduction band, then the oxidization process can be observed, such as the manganese 4 plus and can be changed from the 4 plus to the 5 plus. Okay, so even if this T2 orbiter is far away from the bottom of the conduction band, then the gap between the T2G and the EG is quite smaller. Then we can look at these Tanabe-Sugano diagrams for 3D 3Is in a tetrahedrocyte. We will find such a smaller gap between the 41 and the 42 can have the crossover relaxation. Then such a relaxation can definitely change the luminescence and from the 42 to the 41. So in general, we would like to conclude the luminescence for chromium 3 plus or for manganese 4 plus definitely coming from the 6 coordinate the octahedrocyte. Okay, now I would like to move to the energy level of the 3D. If we have enough this atomic spectroscopy knowledge and we can calculate the energy level of the 3D 3I in 3 states. So it should be kept in mind and we shall input the quite correct values for Raka parameters B and C describing the Coulomb interaction among the D electrons. So, and once these 3D 3Is are embedded into the lattice constants, the atomic multiples quickly will be changed to the crystal field multiples. For example, from the left side and to the right side. Okay, let us look at the point, the crossover point between the 2E and the 42. There is a one dashed line and goes through this point. And the areas in the left hand and the right hand of these vertical data lines corresponding to the weak and stronger crystal field cases respectively. That is to say, in the stronger case, and we just observed this spin forbidden transition from the 2E, whereas and for this weak case, then this quite broadband emission will be observed. Okay, so all these jobs or investigation definitely and moved from the empiric, semi-empiric, and prediction. So first job is about how to understand the linear relationship between these 2E emission energy of the manganese 4 plus in the compounds and with these logistics effect of the magnetic focus. So we give the very deep and theoretical and derivation from the basic formulas. You will find that the predictor and this linear relationship, the form of the predictor relationship, quite close to the results extract from the data mining. So I have to talk about this semi-encrypted model, such as the exchange charge model. We use this exchange charge model to predict the energy levels of this crystal field, the multiples of the magnetic 4 plus or chromium 3 plus in the solids. So here is one example, and we can easily to calculate the crystal field interaction. Then you can see a very good agreement between the calculated energy level and the experimental one. So finally, and from the physical model perspective, I would like to talk about the emission intensity of the magnetic 4 plus or chromium 3 plus. So definitely because the magnetic 4 plus and prefer these 628 the octahedral side. So if you would like to change this emission or enhance the emission intensity, the first idea to change the ligand species. But the shortcoming is then you will change the emission energy. So here we recommended a strategy by using this disorder in the second cation fields. So we can create such a disorder effect in the second cation field. Then we can enhance this emission intensity because this inversion symmetry of the chromium or magnetic 4 plus can be broken. Then the intensity can be enhanced. So if all people would like to understand the theoretical spectroscopy of the transition matter, all various eyes and from free state to the crystal field state, and I recommended this book and for all of you. Okay, so now we shall have the modern version. So the modern version actually is based on the fundamental idea proposed by the Peter Dorenbos. We call it the VRBE model, in which the band gap and the impurity energy level can be determined by the DFT calculation. And you can see in the right-hand corner, one success example about the bismuth. So we calculate the ground energy levels of the bismuth 3 plus and bismuth 2 plus in the band gap with respect to the vacuum energy levels. Then we have to suppose the multiplies calculated by this quantum capture calculation on this VRB model. Then we use such this full energy scheme to understand the transition competition, to understand how to design the luminescence. Okay, so we apply such a method to the 3D 3Is. So it's quite clear to calculate the ground state for A2 of the 3D slide. We just put the 3 electrons on the T2G orbitals. Then how we create the 2E and the 42. So we just make a spin flip on the T2G orbiter to get the 2E. And we also create the one electronic transition from the T2G to the EG. Then we have the 3 systems. Then we calculate the energy difference, total energy difference between those systems to get the energy transition energy. Of course, if we use we employ this Frank quantum principle, we can calculate the excitation and emission energy. So the first successful application is about the physical pressure induced across the crystal field strength in transition of the chromium 3 plus in the potassium aluminum fluorine 6. So with the pressure increasing, the 42 energy just goes up, whereas the 2E goes down. So the interesting part is the crossover point. The crossover point occurs at the 12G power, and our calculation and clearly show this trend and give the quite close to these crossover theoretical points. So the same idea can be applied to the chemical strength induced by the doping concentration of the long luminescent zinc doping to the calcium aluminum germaniums. So you can see these quite similar crossover phenomena. So with these understanding to the energy levels and electronic structures, we would like to evaluate the thermal stability of the chromium 3+ and doped materials. So firstly, and we calculate the formation energy for this chromium 3+. We found that chromium 3+ prefer this octahedral side and by the yttrium. So we also find a great Jahn-Teller defects distortion for 42 stators. Then with our calculated electronic structures, and we can find the illumination center of the chromium 3+ is far away from this electronic band structure of the host. So in the experimenter, we can see the host excitation efficiency is not good enough. So of course, and we also can calculate the thermal excitation manager to explain the thermal quenching. So we know the mechanism of the thermal quenching is because of the crossover between the 42 stators and the 4A2 stators, all these energy surface. So we just calculate the 0 point of the 42 states and its crossover with the 4A2. The calculated this thermal excitation energy is 0.266 electron voltage. This is quite close to this experimental one. So finally, I would like to talk about this site occupancy and the valence states of the manganese 4+ with the chemical potential, or with or among or all crossover the compound species. For example, we choose the CAGG here as an example, and here we just show the formation energy of the manganese ice with the different states, with the different size on this chemical potential, and even on the Fermi energy. We can see here, if we consider this oxygen-rich condition, that means we are under this oxidization condition and environment, then we will see, and the manganese ice will show this 4+ valence state, and always stay this octahedral side. And on the other hand, if we have this oxygen poor condition, then the manganese 2+ will show them in these 8 coordinate and ligand environments. So of course, and we can also use the different raw materials to model such atmosphere change. So here we use calcium oxide, amount of the calcium oxide. So with the increasing of the calcium oxide, we will see this dominant manganese amount of the dominant manganese ice decrease, and the 3+ and 4+ mount and increase. So with such and this tuning this strategy, we can enhance and the turbulent and this 4+ and ice and intensity, and decrease the dominant ice intensity. So here is in concluding. So in summary, I would like to say, so from the first principle calculation, we can predict the geometry, structure, electronic structure, optical transition, and even the thermal stability of the 3D, 3Is, and in the solids. So I would like to show to say great thanks to my collaborators, and of course, and many thanks and for your attention. So after my presentation, I also would like to make this advertisement and for 2 conferences. So one conference in Honolulu, this ECS conference, and another one is this International Winter School held in Chongqing in November 24 to the 26th. So all of you are welcome. I also do appreciate the support of the 2 journals. So one is the Journal of Rare Earths, and the other one is the Optical Materials. So all high quality submissions are welcome. Thank you, and many thanks and for your attention.
Okay, thank you, Professor Ma, for your very insightful talk. Wow, it brings back my old memory. Those crystal field, those Young-Taylor distortion, I haven't heard this since my college time. It's very good. So any?
Thank you very much.
Okay. Any question from the audience? Okay. Due to the time's constraint, because we have a terrible delay, it's not your fault, but it's our fault. Let's thank Professor Mars once again.
Okay, so thank you.
Thank you. Thank you.
Wish us success and good success on the conference. Bye.
Bye-bye. Thank you. Okay, next speaker is Junsha Lee, right?哦，用影片播放。好，只有在线上跟我们互动，但是OK， 只是放影片而已。好，好，好。
Good morning, everyone. I'm Li Chunxia from Shandong University. It's my great pleasure to present my research on photo-functional nanomaterials for synergistic tumor therapy. I will report from the following aspects. Background. As we know, cancer poses a serious threat to human health, and nanomaterials offer promising possibilities for efficient diagnosis and treatment of tumors. The tumor microenvironment, TME, has several features, including hypoxic acidity, high levels of hydrogen peroxide, and GSH. Therefore, the targeted drug delivery and control release by utilizing TME have become hotspots. Nanomaterials are a new type of agents for tumor therapy. Rare earth absorption nanoparticles using A can convert near light into UV, visible, or even near light. Noble metal materials can be used as photothermal conversion reagents to realize photothermal therapy, PTT, and they have multiple enzymatic activities. Compared to UV or visible light, near light offers unique advantages, such as high penetration depth and weak background autofluorescence. These two classes of nanomaterials are suitable for multiple bioimaging. Furthermore, they can be combined with other treatment routes to achieve tumor synergistic therapy. The main line of all research includes the controlled fabrication of nanoparticles, construction of composite nanomaterials, and their applications. Aiming at 3 key scientific questions. First, how to regulate compositions and structure of nanocomposites. Second, mild PTT has limited efficiency. Third, how to reverse immunosuppressive TME and inhibiting tumor metastasis. To address these questions, we have carried out 3 typical research aids. Now introduce the first research, aiming at the composition regulation of multifunctional nanomaterials. We have obtained various photofunctional nanocomposites and realized the effective integration and synergistic enhancement of different functions by reasonable fabrication methods, such as mesoporous silica coating, covalent linking, and polymer coating. The second typical work is about photothermal materials for synergistic mild PTT. PTT works at temperature above 50 centigrade, which inevitably damages normal tissues. So, UVs have been thought to achieve PTT at mild temperature from 38 to 43 centigrade. But cancer cells can activate protective mechanisms such as up-regulating heat shock proteins (HSP) to achieve heat resistance, and thus low temperature PTT therapy is not ideal. To address this question, we designed two solutions. The first is to propose a new concept of phoroptosis promoting low temperature PTT by PD single atom nanozyme. In the normal cells, due to the protective effects of HSP, PTT remains off without any damage to normal tissues. In the TME, the nanomaterials have POD and GSHOX mimic enzyme activities, which can efficiently catalyze the production of RS and the depletion of GSH, leading to the accumulation of LPO and phoroptosis, further inhibiting the expression of HSP to promote the therapeutic effect. Another solution is to design gold platinum silver GOX nanozymes for starvation therapy, enhanced immune PTT, and immunotherapy. Nanomaterials have catalyst-like activity, can ameliorate tumor hypoxia and improve the GOX activity. More importantly, the cut-off of nutrients causes a reduced intratumor ATP level. Upon 1064 nano laser irradiation, mute heat is generated in the tumor area. Meanwhile, limited ATP level can inhibit the synthesis of HSP, thus achieving therapeutic effects of mute PTT, which can enhance the recruitment of tumor-infiltrating lymphocytes, reshape the immunosuppressive microenvironment, and transform cold tumors into hot tumors, thereby improving the response rate. Aiming at how to reverse immunosuppressive TME and inhibit tumor metastasis, we firstly designed UCA-based nanocomedies for starvation, chemodynamic therapy, and immunotherapy. By using enriched hydrogen peroxide and GSH in TME, the production of RS can be effectively increased, which further induced macrophage polarization to reverse immunosuppressive microenvironment. And the degradation of corpuscle S also leads to the recovery of upper conversion luminance of UCA, which can be used for bioimaging. Additionally, combined with PD-L1 antibodies, the nanomaterials enable synergistic immunotherapy. Cell experiments have confirmed that compared to control groups, the proportion of anti-tumor M1 macrophage in UCCG group increased greatly, while that of immunosuppressive M2 macrophage decreased. This suggests that RS induced macrophage polarization to reprogram immunosensitive microenvironment. In vivo experiments showed that nanomaterials could effectively activate the expression of DC, CD4, and CD-T cells, eliciting strong immune response. We further established a bilateral tumor-bearing model, further combined with anti-PD-L1 blockade. The treatment group UCCG effectively irradiated the primary tumors and inhibited the growth and metastasis of distant tumors. In addition, upconversion luminance also play an important role. UCL intensity greatly recovered over time. Moreover, the distribution of the nanomaterial in the body and the degree of accumulation at the tumor sites can be modified by UCL imaging. thus providing an optimal time window for treatment. The second idea is to reverse immunosuppressive TME by pyroptosis. Pyroptosis is a kind of programmed cell necrosis mediated by histamine family proteins. In the classic process, activate caspase 1 can cleave histamine D protein to produce the histamine N domains, which can bind to membrane phospholipids and induce cell membrane perforation, resulting in cell swelling with large bubbles. Cell bubbling and further cell lysis lead to the release of a large number of inflammatory molecules and cellular contents, thereby triggering a stronger local inflammatory response. However, the development of nanoplatforms as pyroptosis inducers is limited. Therefore, we designed several biodegradable pyroptosis inducers. The first example is the biodegradable calcium nanomodulators as pyroptosis inducers. The obtained nanomaterials can decompose under low pH to release calcium and curcumin, leading to a sudden surge in mitochondrial calcium ions, eventually results in pyroptosis. Curcumin promotes the release of calcium from the ER into the cytoplasm and enhances calcium efflux, leading to mitochondrial calcium overload. This further induced the production of RS, release of cytochrome C, activation of caspase 3 and GSDME protein, results in pyroptosis. We not confirm the mitochondrial calcium overload triggering pyroptosis for the first time, but also reveal the robust immune response along with suppressing tumor proliferation and line metastasis. Pyroptosis is a novel form of cell death primarily associated with the aggregation of lipolytic proteins within the mitochondrial tricarboxylic acid cycle. The research on pyroptosis is still in its early stage, and there are many problems need to be addressed. Firstly, GSH severely limits its occurrence. Secondly, the glucose and hypoxia reduce the sensitivity of tumor cells, which is highly dependent on cell respiration for the progression of pyroptosis. Thirdly, by safety of copper carriers. Therefore, we designed a biodegradable copper quinine linker dual X nanocomposite based on Taiji thinking for inducing pyroptosis, kyphoptosis, and immunotherapy. The designed nanomaterials have four enzyme-like activities. By generating a large amount of RS and oxygen while consuming GSH and inhibiting HIF-alpha, it can inhibit the NRF2 NKO1 pathway and break the antioxidant defense mechanism of dormant and recurrent tumors. At the same time, the nanomaterials can amplify the effect by bonding with DOS so as to reverse the tumor immunosuppressive microenvironment. It was found that CQG triggers pyroptosis through a dual strategy. Firstly, the nanomaterials can disrupt NRF2 NKO1 pathway, making tumor cells more sensitive to RS. Secondly, the multi-enzyme-like activity of nanomaterials combined with the starvation effect by GOX, producing a large amount of RS, leading to severe oxidative stress. The tool recruits a large number of NLPR3 and activates their caspase-1 pathway, leading to cell membrane proliferation and release of cellular contents. From WB experiments, it can be found that the expression of NRF2 and NQO1 is reduced, leading to apoptosis caused by the cleavage of GSDMD protein. Cellular GSH and oxygen levels are important factors in regulating apoptosis. The materials degrade into copper ice and quinones in TME. Quinones can undergo macro addition reactions with GSH, while oxygen provided can improve the hypoxicity of tumors. Copper islets can aggregate the LAT in the tricarboxylic acid circle, causing mitochondrial dysfunction and promoting cell death. In vivo 41 tumor models and human-derived tissue PDX model have been demonstrated the good anti-tumor efficiency. The third example is to enhance pyroptosis and cuproptosis through lysozyme rupture-mediated autophagy inhibition. Autophagy is an important protective mechanism of the cells and impairs various therapeutic approaches. On the one hand, it can affect cuproptosis by recognizing and cleaning protein aggregates mediated by lysozyme. On the other hand, it can affect key factors that activate pyroptosis, such as inflammasome assembly and caspase activation. Therefore, we are wondering whether blocking photogauge can increase cuproptosis and pyroptosis. Thus, inspired by the window breaking effect, we designed the copper LDH as a lysozyme disruptor. In acidic conditions, the nanomaterials degrade to release copper ice, leading to lysozyme rupture as the first window, leading to the blockade of photogauge process. The occurrence of photogauge inhibition enhances subsequent cuproptosis and pyroptosis. In conclusion, we have designed various functional nanocomedies which remain inert in normal tissues and are only specifically activated in the tumor microenvironment, achieving synergistic tumor immunotherapy. Firstly, I would like to express my gratitude to Professor Lin for his kind help and thank my collaborators, postdoc fellows, and students for their hard work. Thanks very much for your attention.
Okay, I think because Professor Lee is not physically online, so if you have any questions or comment, you need to contact her directly through her email. By the way, I forgot to mention Professor Lee is from Shandong University. So now we need to catch up time. The next invited speaker is Professor Yu Hai Zhang. Is Yu Hai Zhang online? Okay. Professor Zhang, I have to say sorry to you because we have a back-to-back technical problem in the first two speakers, so the schedule being terribly delayed. So now it's your turn. Take it over, Professor Zhang.
Hi.
Okay.
Hello.
Yeah, I can hear you.
Oh, finally. Sorry,
Also
sorry
see
for the
your
delay.
see your image.
Great.
Yeah, you can
So,
start it.
yeah. Okay. Thank you for your kind patience. And it's a great honor to be invited in such a wonderful conference. My name is Yihai Zhang, the PI of the Lab of Transparent Luminescent Materials in the University of Jinan, from Shandong again, China. Our lab is particularly interested in those luminescent materials that are transparent, including some single crystals, glass, and nanocomposite. For today, I will focus on some progress on the transparent nanocomposite only. In this talk, the synthesis of nanocomposite will be first introduced, followed by the applications in two fields, including the X-ray scintillating screen and the full color transparent display. Now let's start with the first topic, the X-ray imaging. In this area, the transparency of a scintillator is very important. Not only it can reduce the reabsorption loss, but also it can significantly increase the spatial resolution of images. There are three kinds of scintillators, including single crystals and some ceramic glass and phosphor composite. Unlike the crystals and the ceramics, the nanocomposite doesn't need a high temperature sintering, so it's quite convenient to make and quite cost effective. In fact, the first X-ray image was taken by using a phosphor screen 120 years ago. The phosphor powders were first blended with some glue and then cast into a scintillating screen. Such screen was quite bright under X-ray irradiation due to its high phosphor loading. The phosphor loading is always 90% by weight. But it suffers a severe scattering problem. It's not transparent, and therefore the resolution is quite low, only 2 or 3 lamperes per milliliter. Recently, people are trying to make it transparent, but the trade-off is you have to reduce the phosphor loading to less than 5%. Then you have to suffer from a very low light yield and a high dose rate, and therefore a high healthy risk to the patients or the doctors. We have been working on this scintillating screen for several years, and made some progress on perovskite and manganese-based glasses. But as you can see, they are just semi-transparent. They are not fully transparent. They have a very intense green color, which is from the intrinsic absorption of the band gap. In this sense, we have to look for some matrix with very wide band gap. To this end, we choose the metal halide as the host. Metal fluoride, in particularly metal fluoride, because it's quite stable for water. Unlike chloride or bromide, they are soluble in water. This kind of metal halide has a very low phonoelectric energy, and therefore they have a very high PLQY, and they have very wide band gap, sometimes up to 10 electron volts. Guarantee there's no intrinsic band gap absorption in the visible region. In fact, This idea has been proposed 3 years ago by Dr. Xiaogang Liu, my PhD advisor. However, they find a decreased transparency when increasing the nanoparticle content up to 2.5%. As you can see, although the intensity is increased, the resolution is decreased. To achieve a high loading content of nanoparticle without losing the transparency, my student, Dr. Dr. Zhang Xiangzhou proposed another colloidal method. He synthesized a new colloidal that looks like this, looks like white in the beginning. As the water dries out, the colloidal becomes a fully transparent screen film that is crystal clear to human eye. This whole process was conducted under room temperature, and therefore we are able to make a large area transparent screen. Here is the transparent screen. Here is the transparent screen, and according to the TJ measurement, the screen has 83% of solid. 1 minute, please. Sorry for my delay. This film has 83% of nanoparticles inside, only 17% of polymer. And SEM shows its cross-section with closely packed nanoparticles. Then how come such a high transparency? According to the light scattering theory, the transparency has a formation, a formula like this. It has a very strong relationship with the refractive index of the particle and its dispersion medium. If their refractive index matches with each other, or if they are identical, this term gonna be 0, and therefore the transmission gonna be 100%. In the beginning, our colloidal has a lot of water, so the medium has a very low refractive index that is far lower than the nanoparticle. But as the water dries off, only the PVA left, and which has a similar refractive index to the nanoparticle. Therefore, finally, we will get almost 100% transmission in the visible region. Due to the high loading content of nanoparticle, they can absorb a lot of X-ray deposit on them, and this shows a very high scintillating light yield, which is similar to LISO, the commercial single crystal scintillating screen. And they show due to the high transparency, they show the very high spatial resolution up to 122 line pairs per milliliter. Because of its high loading content, it can also perform as a high performance X-ray shielding material. Let's check its shielding performance. this is a Geiger counter. In the very beginning, the count ramps up like crazy. It makes a lot of noise if you can hear, but after blocking with this thin transparent film, it decreases immediately. So this kind of film could be used for some advanced X-ray shielding applications. Now let's go to the second topic about the asymmetric full color transparent display. The transparent The transparent display technique has been widely used in many emerging areas, including the high-end transparent TV, the head-up display, and the Apple Vision Pro, which has gone viral in the beginning of this year. One common thing of these devices is that they are very expensive, right? Because the OLED pixel arrays was used for displaying. Apart from the RGB pixels, they used a transparent zoom or transparent pixel to provide the transparency, which compromised the spatial resolution and the luminous intensity. Besides such electroluminescent OLED, photoluminescence could provide an alternative. For example, Dr. Deng Zhenzhen reported an upconversion strategy to realize RGB color rendering by tuning the excitation pulse. However, the quantum yield of upconversion is too low, sometimes down to 1%, and the excitation laser has to be focused for scanning-based imaging. Resulting in a very low frame rate. You have to take up to 1 minute to make one single frame. So it's not possible for real-time displaying. Instead of the upconversion strategy, Dr. Xia Zhiguo reported a downshifting strategy by using RGB phosphor powders. They achieved a wide view angle, but the phosphor content is only 2% to ensure a transparency, which is too low to provide a decent intensity. More importantly, the RGB colors suffer from severe crosstalk because the phosphors can't be independently excited. In this sense, our transparent film could provide a solution to overcome this crosstalk issue. In our design, green and the red emitters were separately embedded in each film, which shows a high PLK value up to 65%. Then they were bound together using some transparent glue. The salvage film not only remains a high transparency up to 86%, but also exhibited an asymmetric luminescence. That is, under the same UV light, the front surface and the back surface shows completely different colors. More importantly, the color combination can be independently tuned by using two UV light sources. Due to the time limit, I'm not going to go to the details, but eventually we are able to create RGB full color display in a transparent screen through three invisible light sources, and their intensity can be tuned to adjust the color mixing. So here is a video to show the real-time display of RGB pattern. In this downshifting screen, the real-time imaging can be realized because of his high luminescence intensity and high PLQI. So in summary, we developed a high-loading, transparent nanocomposite that is transparent, and we showcased its applications in X-ray scintillating screen and full color display. All these techniques has been patented by my group, and we welcome any kinds of collaboration. Finally, as the supporting editor, I would like to recommend the Journal of Rare Earth to you, which is a pretty good one to the phosphor community. Finally, I would like to thank my group members, collaborators, and the funding suppliers. And thank you. And I'm ready to take questions.
Okay, very nice talk. Any questions from the audience? Okay, I got the general question. Not a general question. My question is like this. I can fully understand your first part. The X-ray film is that's almost completely transparent, right? Because you choose the material has the same refractive index. Your PVA, that's the polymer, has almost exactly the same refractive index as your dopant. The dopant will absorb X-ray. But I still don't quite understand, for your transparent display, your light-emitting material, I don't think it has the same refractive index to the background of your display, right?
In fact, it is. It's
really.
It's the same. Yeah, the phosphorus is exactly the same nanoparticles we used for X-ray imaging. Let's go to some details to this material.
You are using the same PVA?
We are using the same PVA and the same nanoparticle.
Oh, okay.
As you can see, the nanoparticles, the only difference for the color gradient is for green, we are using terbium. For red, we are using EU.
All right.
European, yes.
But they even have a different light-emitting element, but the refractive index still remain almost the same, right?
Right.
Oh, okay. So that's the trick. So you can still achieve the almost a fully transparent display.
Yes.
Using the same principle, the same refractive index material.
Yes, that's the key point. Yes.
Right. That's very good. Very good.
Thank you.
Any more questions? If not, let's thank the speaker one more time. Okay, next is our last speaker of the section, Professor Lei Chen. Professor Chen is from Hefei University of Technology.
Hello, everyone.
Yeah, we can hear you and we see your
I
image.
will play the video. I have sent the video to the committee organized.
Oh, okay. So.
Yeah, in Taipei, maybe it is more convenient than in my office to play the video.
Okay.
Okay, thank you.
Yeah, we'll show your video.
This is the title that I submitted the abstract to the conference organizer committee. Today, my report consists of two parts. In part 1, I will give a simple introduction on this NIR phosphor and LED device. These are the emission spectra of the phosphor synthesized at different conditions, from which we can conclude that the optimal synthesis and composition are by fire at 1415 Celsius degree for 5 hours, with 1% of barium fluoride as flux, and doped 2% chrome as activate. The host has a hexagonal structure in which the gallium, indium, and zinc are coordinated with 5-fold, 6-fold, and 4-fold oxygen. The site occupation of chrome was studied with XRD refinement. However, the result shows that there is no significant difference there. But from the charge balance and ion radiance, the chrome will preferentially occupy the octahedral polyhedral. The SEM shows a typical hexagonal profile of the particles. These are the excitation spectra of the phosphor synthesized at different conditions. According to the Tenable-Scarno diagram, this band is a transition to 42. This band is a transition from 41. However, the nether line overlaps this band, which is a parity forbidden transition to E2. Moreover, there's another wide band, which should be the transition from 41P. These are the absorption spectra of the zinc host and the phosphor. It clearly shows that the host absorption band overlap with 4I2 to 41 transition of the chrome. Moreover, the absorption edge redshift after doped with the chrome, which shows that the band gap become narrower. Moreover, the absorption of the 41 overlap with the absorption edge. It shows that the chrome may take part in consisting of the band edge or forming defect. With more and more chrome doped into the phosphor, however, a new absorption band appeared in the spectra. It may be caused by the non-radiative transition absorption between the chrome and chrome pairs. This figure shows that the phosphor has poor thermostability of luminescence. When the temperature is higher than 100 Celsius degree, the blur band was almost quenched. By combining with the theoretical calculation, it shows that the zinc host has direct band gap with band gap about 3.03 eV. After doped with chrome, the band gap is about 3 eV. The overlap between the emission and the excitation makes the phosphor with low luminescence efficiency. Finally, we packaged some LED devices using phosphor and fabricate an NIR lamp like this. By comparing this figure with this figure, we can find that the NIR has deep penetration. In the part 2, I will share my consideration on photoluminescence, photomedicine, and phototherapy. Because most people have been used to using drugs or surgery to treat the disease, it is very hard for them to accept photomedicine or phototherapy as an equivalent way. Around this topic, there are some interesting questions, such as, do you think light can cure disease instead of medicine or surgery? Can you accept this way? Why are photomedicine and phototherapy necessary, and how to develop photomedicine? As for the history of phototherapy, it can be divided into heliotherapy, light therapy, low-level laser therapy, and photobiomodulation. In ancient, about 3,500 years ago, the Egyptian has used attractors from the weed by combining with the sunlight to treat the vitiligo. In BC 1515, the Egyptians used the sunlight to treat the skin disease. In 400 BC, the Hippocrates has used the sunlight to treat edema. There are also some wisdom recorded in the Chinese medicine, such as the Huangdi Neijing and the Qianjin Fang. As for the phototherapy in modern time, we have to mention the Dr. Feng Shen, who is the first Nobel Prize in Physiology in 1903 for his great contribution in the treatment of lupus vigor using the ultraviolet. This is the world's first ruby laser. The phototherapy using laser as light source called low-level laser therapy. In 1967, Dr. Mist of Hungary found the phenomena of laser-stimulated biological effect. This phenomena was named with photobiomodulation. At that time, the science has progressed significantly, such as in 1916, Einstein proposed the laser theory. As for the contemporary phototherapy, we have to mention the Dr. Michel Hamblin, who is at the Harvard Medical School. He is a dermatologist. The contemporary phototherapy has progressed with quantum science. In 2013, the President Obama announced the Brain Initiative project. In the same year of 2013, a scientist from Russia named with Tina Kazu, she published one paper. Is it time to consider photobiomodulation as a drug equivalent? From the history, we found that the progress of phototherapy strongly depends on the development of science and technology. Particularly for the development of quantum science, it provides us a new way to know about the nature of consciousness and by the way to improve the cognition. In this paper, we put forward a method to develop the quantum medicine. In hospital clinics, there have been many cases of light therapy, such as the blue light treatment of jaundice in children, the retinal photocoagulation, wound healing, and the mevalonine gland therapy. In clinical practice, however, the drugs and surgeries sometimes are not efficient in treating mental and neurological disorders, such as the major depression, the Parkinson's, and Alzheimer's disease. Moreover, as for the natural network in human brain, it is too complex to deal with drugs and surgery. In 2020, one paper published on Science titled with Trials Began for a New Weapon Against Parkinson Light. A paper published by the Hamblin named with Photobiomodulation and the Brain, a New Paradigm. Light offers an efficient way to deal with mental and neurological disorders. We should bear in mind that photobiomodulation is not the simple way that tune the moon with blue, green, or red colorful light. The depth of light penetration into human body is limited. This figure shows the light penetration through a human skull. How to deliver the light into the diseased area, such as Parkinson and Alzheimer's disease? The diseased area is very deep. Is it only possible to cure disease by sending light to the diseased area? No, it is not the merely way. As for the mechanism of photobiomodulation, it is classed into the direct effect and indirect effect, that is called with intracranial PBM and extracranial PBM. The light and photons may interact with human tissues through skin, blood, lymphatic system, the cytochrome C oxidase, and the nanoworld in cells. From the cellular and molecular mechanism, we can find that the absorption band of human tissues are wide. That is to say, the wider emission from phosphorus will be more matchable for the absorption of human tissues than the laser emission band from LED chips and from the lasers. So the phosphorus will have broad future application in for the medicine. Finally, I will report some progress achieved in my group. The first is suppressing the neuroinflammation using the NIR light. The neuroinflammation is widely found in the Parkinson and Alzheimer's disease. These are the emission spectra of the phosphorus synthesized in our group. These are the LED devices packaged using the phosphor. We cultured the microglia cells using the NIR light. The result shows that the NIR light could efficiently regulate the microglia cells from the overexcited state to the resting M0 phenotype and helpfully suppressing inflammation. Moreover, we found that the NIR light could efficiently promote the cell's proliferation and improve cell's activity. The Sjögren's syndrome disease is very hard to treat. We use the PBM method to treat the Sjögren's syndrome using the NIR light emitted by this phosphor. These are the emission of the phosphor and LED device. The pathological pictures shows that the PBM approach is safe. Compared with the medicine treatment using the hydrochloroquine, it shows that the PBM method is more efficient. One most important breakthrough achieved in our group is control myopia. The myopia is considered as not reverse, but our result has achieved a very good result using the PBM approach. Moreover, we take some other researches such as reducing the oxidative stress damage using the NIR light. These are some medical instruments developed in our group. Thanks so much for your attention, and we pay tribute to those phototherapy predecessors.
Okay. Yeah, we all watch your video.
Okay, thank you so much.
It's very nice, very nice. So, any question or comments? Okay, I have one general question. For those near-infrared treated patient, the mechanism of it can kill the disease is due to the thermal damage or due to the photo damage to the back, say the back cell. What's the mechanism inside of it?
Oh, sorry.
Did you hear my question?
Yes, I
Okay.
hear. I hear. This is a very good question. Okay. Wait for a minute. I found the slide. Yeah. Can you watch it? Can you watch the slide?
Wait for a second. We need to put back the
sorry.
PowerPoint.
As for the photomodulation, it does not use the thermal effect. It uses the biological it uses the light biological effect. Impressively, it may use the chemical reactions in the body.
that chemical reaction induced by the near-infrared?
Yes, such as the neural light can accelerate the speed of the blood. With the neural light can stimulate release the neurotransmitters such as dopamine and the neural light can repair the hurted neurons and cells and promote the growth of cells and neurons.
That require the near-infrared. Near-infrared can do the work.
Yes, yes.
Okay,
It
right.
does not use a thermal effect. It may use a biological effect.
Okay, okay.
Okay, thank you so much.
Yeah, thank you very much. Let's thank the speaker one more time.
Okay, thank you so much.
Okay, bye-bye.
See you.
I think it's all done. Well, let's thank all the speakers in this section again. Okay.